So this is Syntactic Elements V1.0 with James here, and it's primarily focused on Grasshopper. And the idea for this is to see the process of designing all the way through to thinking about fabrication and documentation for fabrication. For a real installation, an installation that James and his team Emergent Design actually have built and installed in a really nice, I'd say like low tech, low cost way, which I thought was really interesting. So James, he's a co-founder of Emergent Design. He's a Boston-based computational designer and co-founder and director at Emergent Design, a design technology company focused on delivering computational solutions for complex design goals in the fields of architecture, design, and engineering. Inspired by the combination of mathematics and beauty of natural phenomena, James's work explores applications of generative form, rule-based systems, graph theory, and traditional computational geometry algorithms to draw a bridge between formal product design and current digital design paradigms. Without further ado, I'll hand it over to you, James, and also your cat, which some people are very enthusiastic about seeing in the background there.
Yeah,
and
he'll come and go.
And yeah, so I'll be here the whole time. I'll try to answer as many questions as I can. If you need anything, just call out to me. If I see anything wrong, I'll call out to you. And yeah. Oh, and before we start, just as a reminder, if you can put on bifocals, otherwise you'll get 10,000 messages.
I know, it's the first thing in my notes.
Okay. All right.
Great. I'll share my screen. I'm going to turn off my video as well, just so that it's not in the way of anything.
Sure, I'll do the same.
Okay, guys. Welcome to Syntactic Elements V1. So today we're going to go through the workflow for designing and fabricating this installation that Emergent Design did called Corelight. It's a strip-based direct mesh fabrication workflow. So we took a triangulated mesh and directly replicated that with paper strips from the laser cutter and joined them using binder clips. So like Mike said, it is a very low-cost method, but this could be extended to multiple types of materials like metal plating, sheet metal, composites, but it works just as well with paper. So anything that is like sort of like thin sheet, you could account for thickness. But so here's some images of what you'll be able to produce using this script, and the final deliverables or outcomes from this webinar, you will have ready to fabricate files. So you could really make your own version of this right at the end of today if you have access to a laser cutter. And that would be really cool if someone actually built something from this webinar. All right. So first things first, we are going to open up Rhino. I'm in Rhino 6. I hope no one's in Rhino 5 because there's some C# stuff that I can't guarantee will work. Rhino 7 should be fine, no problems. If you are in Rhino 7, you can probably use TryRemesh instead of MeshMachine, which was one of the plugins listed that I said you needed. But I think other than that, everything should be about the same. So in Rhino, we're going to want to open a small objects inches. That's the one that we're going to use. If you use something else, I don't know, hopefully you don't use like feet inches, but anything else, despite scale differences, I can't guarantee like everything works exactly the same. My Rhino takes a while to open because it automatically opens Grasshopper, so just give it a moment. Okay. Here we go. Make sure those are nice and snapped. All right, I'm going to change my view. Well, okay. So first things first, I got to move this little. I have a little bar for the Zoom meeting. first things first, let's go into the properties, make sure everyone has the same tolerance settings, because I don't want any issues with tolerance issues like later on when we're doing stuff that is like actually dependent on that. So make sure your model units is in inches, and we're going to set the absolute tolerance to 0.001 and the angle tolerance to 0.00. Oops, sorry, just 0.01 degrees. And the display precision, we'll put that to 4 zeros. So this is what your units and tolerances should look like. If you don't have it like this, maybe some things won't work exactly the same. So make sure you do this first things first. All right. What we're going to do first off is we got to build like a little environment kind of, and to place this installation into. So when we were doing this, I might even just minimize Grasshopper for now and maximize Rhino. Okay, great. I'm going to go ahead and just take like a box component and start at 0. And instead of building things in the positive XY, we're going to use this space later. So I would say build things in the negative XY quadrant. And we're in inches, so we're building like a life-size thing, a big installation size thing. So maybe we do like 12 feet by 12 feet, right? So that's like 144. Got to do negative 144 and negative 144, right? Okay. And I'm going to put it, instead of going up, I'm going to put it facing down. So I'll just do -1 inch. This isn't anything important. This is just the like base. But you see if I go into the front view, it's at 0 to -1 and not sticking up above the ground plane. I'm going to put it in shaded view so you can get a little look. Zoom onto that. OK, so we got this little platform. And this will just be like representation of the floor that we're going to build this thing on. And let's get some walls in there too. I'm just going to copy this and rotate it. And I will move that to this corner here. Let's see, did I get that right? Yep, that's good. Maybe I'll mirror this over. And you don't have to follow my things exactly. Oh, my mid thing isn't on. You don't have to follow my build exactly, and especially when we start making the actual installation, it would be better almost if everyone did their own thing. I'm just going to build like a little cube, or a little cube with no ceiling. Oops, I didn't copy that. Okay, that looks good. That's what I like. I'm going to highlight these and set object display mode to wireframe, just so I can see inside of this thing. Highlight this and zoom selected. All right, we've got a little sort of environment here. I'm going to name the layer that we're on right now, just environment, right? And that way, we're going to name all the layers like something that makes sense, and instead of just the default layer names. Right, so now that we've got this like little life-size space, right, 12 feet by 12 feet, that's large enough, I think. We can open up GH. Let's get that open. First things first, I'm gonna drop in bifocals. Let me put that right up here. And everybody open up that all C# script components file that was downloaded, the downloaded file. Everybody open that, because we're gonna need to get some stuff from there. So first thing that we need is this orient people to screen, this whole group of things right here. We're going to get this. And this is just to help us visualize like the scale of things as we're building out the basic frame of this thing. So let me enable this. Right. Your guys probably won't be in the exact same place. So the way that this works is like we have this curve, which is this lady profile right here. And I've already got it scaled for like appropriate human heights in inches. So you don't have to mess with those if you're in inches. And these points here, if you preview those, that's where you can move these people around. And the reason we've got this whole thing here is just so that you notice that as I rotate around, the people stay facing me, even though they're 2D profiles. They stay facing me. This is just like a nice thing that I like to have in some scripts when I'm designing something that's going to be like actual human scale, so that I know it's not going to be like too short for people to walk under or something like that. So we'll just leave these guys in here right now as we are going to design the skeleton of this shape. Basically, we're going to start with a skeleton. I'm going to come into the 2D view so I can just show you something here. We're working with a component called Fattener, and it's from Daniel Piker. And the way it works is, let's say you have like some lines, right? And you have maybe 3 lines joining at a point, or 2 lines joining. This right here, this intersection here, that is a valence 3 intersection, aka 3 lines joining to create, one vertex. Valence 3. This is a valence 2. What you don't want to have when we're building the skeleton is anything that has more than valence 3. So you don't want this. A valence 4 node won't look good when we use fatten. So just make sure to keep everything to valence 3 or less. All your connections should kind of look like this when we're designing the skeleton. And you'll see when we start with the fattener component why that is. It doesn't topologically create like a good mesh when you have more than 4 lines meeting at any vertex. So here's where you can kind of just be creative. I'm going to start by putting a point just in the dead center. Let me get my smart track on. Put a point in the dead center of this thing. Come on. Yep. Get that there. Oh, hang on. At that point, we're going to move to a second layer actually, and we're going to call this like skeleton, or you can call it like line network. This is where we're going to build the curves that become what we input into Fattener. Okay, so now I can grab the midpoint, grab that midpoint, put them together. I'm just going to draw a line across from the top, so I can now draw a vertical line from here to here. I don't need this anymore. All right, we've got like a central kind of line here. I'm going to divide this into like 5 segments, right? So you got now 1, 2, 3, 4, 5 segments. At this segment, I'm going to draw a line. Let me go into the front view, draw a line that comes to, let me put on project, draw a line that comes to here, I guess. This should be moved in. What is the, oh, geez, I hate that. Okay, we're going to draw it down to the bottom and then move it up, right? So I'm just trying to draw something that goes from the base to there. Now I'm going to move it from here to here. Right, this is what I wanted in the first place. I've got this little curve now, and you see that this line, and this line meet at this vertex right here, right? And that is a valence 3 vertex. Even though it kind of looks like these are 1 line, they are 2, and this is the 3rd line. I'm going to copy and rotate this and move it to the top of the next one. And you definitely don't need to design the same thing I'm doing. I'm just doing this because it's kind of fun to have like a central pillar. It'll probably look pretty cool. But the original one we had just backed up against 2 walls in a corner. It wasn't like in a box like this. We had it so that you could like walk under it and through it. Copy this last one up to there. All right, check that out. Looks kind of cool. Okay, I'll delete this point. Don't need that point anymore. Right, so back in here, I'm going to actually just like instantly save this file. I'm going to save this for, I'm going to call this form finding. And we're going to do kind of 2 files here. One is going to be all the form finding stuff, and one is going to be all the like strip making and labeling and fabrication data type stuff. So if you leave this on, you'll always get the star when you hit save. See, now it doesn't come back, but when I turn this on. So don't worry about that. You did save. It just, if the timer is going, it'll say that it didn't save. Right, so first things first, we are going to drop in a curve component. And with that, we're going to set multiple curves and grab the curves we drew in here, reference those in. And now we are going to take a fatten component. And this one's pretty key. So if you had trouble with this, you're going to hit a roadblock like right away. I'm sorry about that, but this is just a really good component for this. We're going to set, I guess I will always use panels so people can see the values of things that I'm typing in instead of just directly typing in like here. I'll put it outside in panels. So we're going to set the thickness to 12, which is 1 foot. And the length subdivisions, we're going to do 0. And the end type also is going to be 0. We want it to be open, not pinched or capped or spikes. So let me get this. Set this to 0. Length subdivisions and end type. And now you see the nice looking thing. I mean, it's not so nice looking right now, but right next thing we're going to do is going to make it look a little bit better. We're going to get the Catmull-Clark subdivision. This is important to use this one, not the loop subdivision, because Catmull-Clark always continues to make every face a quad face, which is very important for the relaxation step that we're going to do here. We will triangulate it later, but for the Kangaroo stuff, we want it to all be quads. So we'll plug that in. I will unpreview this. That looks pretty good, but we're going to set the level to 2. I'll just grab this again, copy that over, set this to 2. Right? Smooth naked edges should be on 1 automatically, but I'll just make sure that everyone knows. Right, so you'll notice that it's just all still quad panels, no triangles, and that's what we're looking for. And that's the reason we used Fattener for this. This topology is like really, really nice and allows you to do some stuff with like a bit more intention than what we have already done. And don't worry if your thing doesn't look so cool. Like this doesn't look that cool either. We're definitely going to come back and change it in just a bit. Once we get the Kangaroo stuff all set up, we'll be able to like relax it and see what it's going to look like, and then go back and edit the skeleton so we can make those changes that we want to make it look really cool. So first things first, let's get a Kangaroo solver, right? Make sure this is from Kangaroo 2 and not Kangaroo 1. That's something I have to check all the time because I've got like a million plugins. We're going to get the toggle for the on, and we're going to get a button for the reset. Ooh, okay. We're going to need an entwine component also that will hold all our goals. We're going to get a few goals. It's not so complex, but we're going to have a few. I just leave the threshold and the tolerance. Don't worry about that. We're going to have 5 goals. So let's up that to have 5. Remember, it's index space, so 5 means the last number is going to be 4. First goal is obviously we want to see this thing. So let's get the show goal or show component. Not really a goal. We'll pop that in to the first one. Then we're going to need to get some edge lengths. Yep, edge lengths. We'll get that right here. The length factor, instead of 1, we want it to be 0. That'll make all the edge length targets, like they'll sort of act like springs at that point. Strength is 1 automatically. Just leave it at 1. That'll go right into the second goal. The third one is going to be an anchor goal to anchor the naked edges. Let's make sure I'm getting them all from Kangaroo 2. And we'll plug that in. But we're going to need the points. So for that, we're going to come up here and get the naked vertices. Where's that? Oh, okay, so it is in the mesh thing. I just didn't see it. All right. Yep, we're gonna get the naked vertices because that's the important thing that we need to get from this mesh. And that's the reason we have the ends opened. If you see here, and I put this in the point, it's just the edge ones. That's why we don't want the ends to be closed. We want them to be open. So we need these to stay put when we do the relaxation step. So we got those, put those right into the point. The target can be left empty because the initial location is what we want. Let's turn the preview off of this. And the strength is 10,000, and we'll leave it at 10,000. That's good. I can actually, yeah. All right, the next one we're going to want to do is the smooth goal. Let's see here. Smooth. Yep. Make sure that's from the right Kangaroo. Yes, it is. Pop that into 3. The mesh that we want to smooth is the mesh. And the strength is 1 here. We're going to up that to 10. If you don't see something sticking out of one of these inputs, that probably means I left it as the default value because I'm really trying to be aware of making sure I label everything. So if it is not labeled, it's probably just the default value, like the target and strength here. They're just the default value. OK, so let's see if this runs. I know we're leaving one goal out. That's on purpose. Let's minimize all this. And let's get a bang component, the explode tree, because we have a few things that we don't need, and we only want the mesh. And that's why we put the show goal as the first goal, so that it's the very first mesh, right? So we're going to put a mesh component this so we can visualize it without seeing all these vertice points. We will turn that off. OK. Right. So you see it pretty instantly converge. It's really a simple thing. And the reason that we chose all the valence 3 vertices, nodes, for this line network is so that things join like really nicely like this. So we've got this like crazy kind of looking springy structure here. But you'll see that it gets quite skinny at points as it's being stretched. Like I don't like this cross section of this area here, a little too skinny. So that's what this last goal is going to be. We're going to put in a rod goal. And that is why another reason we used the fatten component. You get really nice edges that are like either this direction or this direction. You've got the warp and weft directions. And that's just important to have. So we're going to need to get those because we want to treat them differently. Like we don't want to make it stiffer along this way, but we do want to make it stiffer along the cross section so that we don't get it squished like this. We want to stay fairly circular, just so it doesn't get like real skinny. So we're going to get the warp and weft. Make sure that's the Kangaroo 2 version. Right. Put the mesh into that. We're going to join these curves that come out of the. Well, let's make sure that we get the right ones, right? Yep. So we've got the right ones are the weft direction. You'll see that if I plug this into the warp direction, those are along the mesh, and we want the ones that go sort of across the mesh, I guess. A little weird to look at because we're looking at the pre-relaxed lines, but I think it's easy enough to see. We want the warp component outputs. We're going to put that into the join curves, so each of those edges is joined into a polyline. And then we're going to put that into the polyline input of the rod goal. I will hide these. The length factor is 1. Angle factor is 1. Axial strength is 10. And the bend strength is 1. We're going to change a couple of those. So let's grab a panel. I'm going to type in 1. And the axial strength is 10. We're going to lower that to 1. We don't need the axial strength to be like that. And the bend strength, we're going to set that to 100. So comparatively, its very strong bend strength. Right, that's going to go here. And you'll see that it's a little bit sort of,
Hey, James.
it keeps the cross sections good. Yeah.
They're just asking if you could zoom the grasshopper in just a bit.
Oh, sorry.
There,
All right.
just so they can read the name.
Yeah, let me get the chat window open so I can see stuff like that.
That's right.
Okay. Yeah, I see it now. All right. Sorry, guys. Is this a pretty good zoom level, you think?
I think you can go out a little. I guess pretty close.
All right.
See.
I'll try to.
One more
yeah,
out, maybe.
I'll stay in.
Yeah, like somewhere around there.
Okay, no worries. Yeah, I usually like kind of stay a little zoomed out. All right, so now we've got all our goals set up. And look at the difference when I disable this rod goal. Just watch on the Rhino side of the screen. Things will get a lot skinnier. And that's just what we don't want. This is a pretty okay shape, you know, so things don't get too skinny. Like we're not stretching anything really far. But as we modify it now, which is what we're going to do, things will sort of get a little skinny if we don't have this goal. So, okay, now that we've got this all set up, we can go back to the skeleton and sort of edit some things. Like I kind of think I want to join maybe this lower branch with this upper branch so that we get like a hole in the middle here. So the way I'll do that, if I can close this out, you'll notice that this is one line, right? If I divide that into just two segments, there and there, and I'll divide this one as well. And now I can draw a line from this one to this one, and that's a valence 3 node. See, right there. This is valence 3, that's valence 3. Just every connection should always be a valence 3 node. And now let's put this in and see what that looks like. So you'll see how things can change pretty fast when you do this. Right, look at that. That's kind of cool. Got this nice central hole there now. That's fun. And maybe I will join these two as well. These two. So I will divide into 2, divide into 2. And when you do that, Fattener doesn't know what to do with it. You'll see it turns orange. So all you have to do is reset those curves in the component. We'll take this and join it just like we did on this side. Let's see what that looks like. Maybe that doesn't look cool. Maybe it does. Let's check it out. Ooh, that's kind of nice. You get another little hole there. It's kind of cool. So this is where you can like just play around. And something really important though, that I will show you now. If the end lines, like the parts that come join to the wall or floor, aren't normal to the surface that they join. See how this one is coming off angled, the mesh does, but the line is straight. If I were to take this point here and move it down so that that line is not straight, you'll see that the end of it is no longer flush with the wall, which is not what we want. So make sure that every single one of your lines, I got to reset this. Every single one of your lines is normal to the surface that they join to. Just the outer ones, just like this one and this one. They have to be normal to the surface. Otherwise, the opening of the mesh won't be normal to the surface, which if you're building this would make it a little bit more annoying to have connections and things like that. With this, it makes it easy if the ends are flush to the walls to just build like a mounting bracket out of some material. This looks kind of cool. Maybe I want to split this hole in half again, so I can preview this. I think that would be this curve and this curve. Maybe that'll be cool. I will try it. Let's divide into 2, and I'll divide this into 2. And let's see if I put a line from here to here. That might be a little too much. Might get a little tight. We'll see. Set those curves. What do we got here? Ooh, I do like that. 3 holes in the center like that. Kind of cool. I think this is what I'll stick with for now. Yeah, this is nice. Great. Don't go too crazy with this. Like you don't want any like really tiny holes. Like if you start subdividing all these things like over and over again, you'll get some really tiny holes. And later we're going to have some geometry that might stick out into the holes. So you don't want to make it hard on yourself if like you're actually going to fabricate this thing. Like there's no reason to make things a little too tight. This guy's head is sort of like inside of this thing. So maybe I'll move that guy. Very nice. Oh wait, wrong guy. Look at that. All these guys, they're just enjoying the art. It gives you a little sense for when you're making this skeleton, sort of like the placement of the members of these like branches, just so you can see how a human might interact with it. Like someone might be able to walk up and stick their face right in this hole here, which would be like kind of cool. All right, now we are going to move into the MeshMachine remeshing. If this looks cool to you guys, I think this looks cool for me. I hope you guys have done your own sort of skeleton design thing here. Like, let's say these 4 branches hit the walls, this one hits the floor, and this one is like tied to hanging from the ceiling or something like that, some beam or something like that. Actually, let's see what happens if I just get rid of this entirely. Do I like that more? Kangaroo will get a little stuck on some points at certain points. Is this cooler? No, I don't think this looks cooler. I'm gonna put that back. Right, that looks good. I find that at this point, the people orient cluster kind of starts to make it go slow. So I'm just gonna disable it. You don't have to, but I'm gonna disable it. I already know that it looks fine for human scale. So that's that. I'm gonna save this. We're gonna move to a new layer, and I'm gonna save the Rhino file at this point because I don't want to lose that. That would really sink. Save this as working. It's really the Grasshopper files that do most of the stuff. We're really just using the Rhino file to like hold some data, like the skeleton and the environment. But we're really going to do most of the work in Grasshopper. So we're going to name the Grasshopper stuff like the steps that we're doing. But the Rhino file is really just the working file. So that's how I name it.
Hey, James,
Right.
They're asking if you can share the file like at a certain point, like maybe when is this a good stopping point? Like share it just for the next part. So
yeah, sure, for sure. How should I share it? Can we just put it in?
It's up to you.
I mean, like in Zoom or Dropbox?
Dropbox is probably better.
Okay. Yeah,
you can either send it to me or you can put it in your own Dropbox and just put the link into the chat. Up to you, whatever's easier.
Okay. Yeah. When we are finished with the like form finding stuff, there'll be like a kind of a break point where we are then going to move into like all the strip making stuff.
Yeah.
And so then I think that's when I can share the file.
Cool.
The Rhino file, huh? Not the Grasshopper file?
I think both.
Be both. Yeah. Okay, I'll do both.
Like nothing.
Yeah. Gotcha. All right. So now what we're going to do is remesh this into triangles. It's nice that we had all the nice topology. I'm going to minimize or hide the skeleton just so I can't see that anymore. Don't need to look at that anymore. Okay. So we got this looking good. We're going to go into the triangulation phase. It was nice to have it in quads because we were able to separate the warp and weft directions for that rod goal. But now that we are, it's sort of a really tough shape to planarize as quads. So that's why we're going to remesh it into triangles. Another added benefit of triangles is knowing that we're going to laser cut these as strips with tabs for actually assembling. All triangle strips will be able to lay flat because each triangle can lay flat, and thus you can lay flat an entire strip of triangles as long as they don't like come back around on the end of themselves. So we've got to get the MeshMachine. MeshMachine, and here's where if you use Rhino 7, like I think you can use the try remesh component, but I'm not on Rhino 7, and I can't guarantee. Right. So we're going to need to get the mesh into the geometry. We're going to need to get a button for the reset. Whoops, there we go. And a timer component, which I will set to 20 milliseconds. Turn it off. Don't need it to run while we are still setting things up. Right. Oh, sorry, I was a little zoomed out. Almost forgot. The length, remember we're in inches, so this is the target edge length of the triangles that are going to be formed from this. And we don't want the triangles to be too big because then the strips will be like too large and you'll only be able to fit a few strips on a sheet of material when you're like fabricating this. So when we did Corelight, I think we did about 4 inches for the target edge length. I think maybe I'll do like 3 inches. I will get rid of the name so you can get the name from there. Move this down so everything gets nicely aligned. I kind of like to be really neat with my Grasshopper scripts. Fix curves, we are going to want to get the mesh edges. We don't want the naked edges to move at all when we do the remeshing. So let's, from the mesh that we've generated here, join the naked edges. And we should have 6 polyline curves, which are the open ends of the shape there. We don't want those to move. Nice. We don't want those to move at all. So let's get those into the fix curves. Since we did that, we don't need the fixed vertices. That would be the naked edge points. I guess you could do it either way, but it doesn't really matter. Yeah?
I just want to make a comment because Max asked, where does timer come from? In Rhino 7, they renamed timer to trigger.
Oh,
and it looks a little bit different. But yes, and if you're using 7, which I assume it's called trigger.
Everyone get your fancy timers out.
And then is Rhino 7 or other point? I don't have the goal component, for example. Goal. I think that's all pretty standard.
Yeah, I didn't use any crazy stuff. This is all just definitely from Kangaroo 2. Yeah. I don't think Kangaroo 2 changed, did it?
Yeah.
For Rhinoceros?
I don't think so, no. But it comes with 7. So
right.
I don't know why you wouldn't.
You should have it, all these components you should definitely have. I guess we'll see if you just can't find it when I send you the file, you know, when you open it. Pull strength, it comes in at 0.8. We don't want any pull strength, so we're going to set that to 1. Whoops. Comically large panel. Pull strength at 1. And everything else is good as it's, everything that doesn't have a thing plugged in is good as its default values. That's fine. We need to now get a plankton mesh thing, which I believe comes with this because this outputs a plankton mesh. And then we get a regular mesh, which we'll be able to convert that to it. Hide these. I will now hide this original mesh, preview off. And we can start this. And you'll see it change into nice triangles. Sometimes you get like some weird results from just the original thing. So I sort of like to like drag this up and down. It's more noticeable on like a flat planar mesh because you got like some like repeating patterns. On this, I guess you probably wouldn't see it, but I like to just like move it back and forth a little so that we make sure that everything is like quite regular. Sometimes you'll notice some repeating patterns if you just take the first result on a more noticeable on a flat planar mesh. This looks pretty good. You definitely don't want to go too low with the triangle size either, because that'll just make things a little bit harder later on. If you have like so many triangles, it'll mean you have a lot more steps later on. So maybe we'll change this to like 3.5 inches. Seems pretty good. Yeah, look at that. All right, I think I can stop this now. And we've got our triangulated mesh where the ends are still flush with each surface. All the openings are normal to the surfaces for creating mounting brackets if you wanted to. And all the triangles look pretty good. Like there's no like very large or very skinny triangles. Things look pretty good. And you don't have any weird bumps. I mean, you kind of can see on the edges of things. It's not going to be perfect, but that's just a part of triangulating. Maybe the trireme mesh component does this better. I bet it does, honestly. MeshMachine is pretty old. So anyone using dry remesh is probably going to get a nicer result. Like you might not have these bumpy edges. Okay. Once we've got those, if you noticed in the pictures here, you'll see that we have some like petals. That's what we call these red things. And you see they stick into triangular holes. Now, not every triangle is going to be a perfect equilateral triangle. In fact, probably none of them are. You'll see that a lot of them are just like isosceles triangles or whatever. And we don't want to have, you know, a billion unique petal geometries and holes to cut for each triangle shape, like for each mesh face shape. So we're going to create a typology of triangles for the holes. They're going to be equilateral triangles, just aligned to one of the edges of the face. So you can see here, if I maybe should zoom in a little. Let me find one. Like this face here is a very not regular triangle. Like it's clearly a scalene triangle. The triangle inside it is going to be an equilateral triangle for each face, always an equilateral triangle. And we'll only have 3 different sizes of triangles too. This will help us later when we need to fabricate these petals. We don't have to worry about like labeling them to know which petal goes to which face. All you need to know is there's 3 sizes of triangles, 3 sizes of petals. So it should be pretty easy to slot them in if you're actually building this. So, all right. We are going to start by creating the holes on the triangle, on the mesh, sorry. First, we're going to need to just do a quick save. Let's get a quick save going. And I'm going to actually bake this mesh, right? I'm going to bake it to layer 2, I guess. Layer 2, just so we don't accidentally change anything. I don't want to do all this work and then like accidentally reset the Kangaroo or MeshMachine and get a slightly different mesh at the end. So we just have this one unlock. I need to flip it. Oops, I need to flip it. For some reason, it was inside out. It helps to have your display things so that you can see whether, so you can visualize the back faces of something. I don't know where my display settings are right now. It's kind of annoying. The little computer screen. It's usually up here. I don't see it anymore. Display, there it is. This is what I'm talking about, color back faces, so you can tell if something is inside out or not. That's what you should have going for this, because sometimes, for some reason, things get flipped around, and I really just don't know why. But it happens with MeshMachine. It happens with other things. We'll call this layer mesh. I'm going to change this color from purple to like a nice lavender. That looks good. I like that. We're going to move to a new layer. I'm going to lock this, and I'm going to lock the skeleton. I just don't want to accidentally move anything. And you can see how, you can almost see the skeleton, like how it relates to the shape. It just sort of like pulls everything in tension to be a more relaxed thing. Right. OK. So layer 3, we're going to call this triangle holes, because that's exactly what they're going to be. These are going to be the holes for the petals that we're going to insert later. Maybe I'll turn this yellow. Probably be a little easier to see on top of this lavender, but we'll see later. OK. Going to get some face boundaries from this mesh. First thing, we need all those triangles as polyline curves. That'll help us. And we need the face centers, or face normals is what that component is called. We're going to use it to get the face centers. Right. That looks good. OK. Then we're going to get a point component, and we're just going to make a point This is going to be like our attractor point that we're going to use to size the petals. So let's put that somewhere that it might produce some interesting results, like somewhere close to one of these holes or something, maybe. Yeah, that'll be cool, probably. Right. This point will just be our attractor point. Don't worry about it right now. Where it is, we can move it, obviously, move it later. Don't need to look at all those face centers either. Right, so let's get a distance component. And we're going to check the distance from each center, face center, to that attractor point. We're going to get the bounds of those distances so we can find the shortest and longest distance, right? Come on, there it is. Yep, so the furthest one is 103 inches, the closest is 10 inches of these faces. We're going to remap those so that we can get it from 0 to 1. So we're going to take the value in from the distance, and the source is going to be the bounds. And the target, we're going to leave at 0 to 1. So now we've remapped all those distances from, like 10 to 100 to 0 to 1. So the closest one is going to be 0. The furthest one is going to be 1. Easy. We're going to grab a larger than component. And this is how we can check some distances from here. Let's get that mapping, those map numbers from 0 to 1. And let's put a 0 to 1 with 4 decimals. This is going to be the, I guess, outer border for holes. Maybe we'll rename that. I'm not sure. Check that as the number that we're checking against. You can just leave it at 0 for now. Now we're going to get a couple dispatch components, 2 dispatch components. The first one is going to take the list of face boundaries from back here. Get those. And the dispatch pattern is from this larger than. And you can preview that where we can see now if I move this slider, it's going to only select ones that are so far from the point, right? The distance from the point as based on if its remapped distance is above this threshold that we're changing right now. And the second one is going to be from the numbers right here. Dispatch pattern is from the larger than. And now we're going to take a smaller than component. We're going to check these numbers against another slider, but this one is going to be called the inner border for holes, right? And this is going to work pretty much in the opposite way of the larger than. And we need a third dispatch component. Get this from here. So now we're whittling down that list. If I move this up, right, you'll see that now we've got some out of here. And we're going to take that list from the smaller than component. And let me get geometry so we can just preview this. Right, none of them are going to be smaller than that. Here we go. This is what I'm talking about. So you can now make like a range of faces that are farther than or closer than. Actually, I think I'm going to switch these because I think I wrote those backwards. This is really the outer border for holes, and this is really the inner border for holes, right? Let's turn off the preview for everything but this last geometry component. Let's check this out. If we leave that at 1 and this at 0, you're going to get every single one. Now I can turn this down and change the range of these face boundaries that we're grabbing, and I can change the inner range. So yeah, so this is the inner border for the holes, I guess you could call it, and this is the outer border for the holes. And it's based on a mapping of the closest and furthest face. So it's not based on distances. That's why these only go from 0 to 1. And that's why I like the remap component. You can just change everything from 0 to 1. And it just makes it a little easier instead of having grab all those distances and using the bounds and stuff like that. to look a little nice. Okay, great. We've got these. Maybe I will actually bring it in a little bit. That looks fine there. We're going to get the polygon centers. You could use the area component, but I mean, it's such a simple polyline. You might as well always use the polygon center component. We're going to get that from the holes that are in the list A dispatch, right? The ones that we have left after cutting off the range. These are the face centers of these things. And we're going to get a distance component. Yep, another distance component. And we're going to check the centers of these against this original point. I don't want to look at this ugly wire. I'm going to turn it to faint. Hope that's okay. So if you didn't catch that, now it's going to be hard to, so I'll say it again. We're going to take the centers into the distance component, and the point we're checking against is, once again, this attractor point that we have here. I just set the wire to faint because it goes like across all of these other components, and I hate crossing wires. Right. We've got that. We're going to grab the bounds again of these distances. We're going to, once again, remap. This is how we're going to choose the hole sizes. Like I said earlier, we're only going to have 3 hole sizes, hole typologies. You could have more than 3, I guess, but it just makes it easier when you don't have like a bunch of unique triangles when you're trying to fabricate these petals, because then you don't need to label which face goes to which petal. We're going to take the distances, and the source is from the bounds, just like we did last time. And the target is not going to be 0 to 1. We're going to construct a domain. Oops, construct. Come on, I got too many plugins. Right, construct domain. Move that down so you can see the name. And this is where we're going to set the hole sizes. So maybe I'll just do from 0 to 1.0 again. This will be the biggest hole size. Copy that and make the smallest size, right? So we'll take the biggest hole here, smallest hole there, bada bing. And we'll set this to like 0.75 and this to 0.25. Good, good. That goes into the target there. So now what we've got is the distance of all these remaining face centers to this point remapped to these values, 0.75 to 0.25. And that will let us sort of decide the polygon hole size, the triangle hole size that we're going to create. But first, we need to get a range component, and the domain is going to be the same domain we just created. And the steps is just going to be 2. And this is how we're going to make 3 hole sizes. So if I pop a panel here, you'll see that we have just 3 sizes, like 0.75, 5, and 0.25. If I change these, it will like interpolate that middle number to be the one that's just in between these two. And if I set this to be like 3, now you'll have 4 hole sizes. These will be hole sizes. Right now they're just numbers, but they will become the hole sizes. So you can see how that works there. We're going to take the round to nearest, and that's from Pufferfish, pretty sure. Yeah, this is a pretty good one. Take these numbers that are the distances, right? The numbers y are going to be this range, and remap x, we're just going to leave it to false. So now you can see the values from these distances are converted to the closest number from this list, right? So it'll be clear when I show you this. So now every number is going to be one of these hole sizes, right? Either 0.5, 0.25, or 0.75. So this is nice because now we don't have a bunch of, you know, like a gradient of hole sizes. They're all going to be one of the sizes that we want. And maybe I'll even just leave this panel here so we can see Topologies. You don't need to see the paths. Okay. Beautiful. The whole typologies. And that way we can refer back to what these sizes are if we want to change them later. Right. So now we're going to need to get the planes because we're going to want to create a polygon. This is how we're going to create our triangles. Segments. We don't want a hexagon. We're going to set, I'll use pen. Don't want anyone to not be able to see what we're doing. Set this to 3. This triangle has 3 sides. Boop. Right. We're going to need to use the radius is going to be from these sizes. That's why these become the whole sizes. We'll set that there. And the planes, we're going to need to make planes from each of these faces. So that's what we're going to do now. So we're going to step backwards a little so we can start doing that. Where do I start that? That's at the right after the smaller than at this dispatch, right before the polygon center, right at this dispatch. You want to get, maybe I'll just put a geo component so I can move things down without the wires getting all disgusting. Move things just like below, sort of. And we're going to explode those curves. These are just the, oops, I plugged into the wrong thing. It should be from the list A output from the polyline of the face boundaries, right? Explode those. We're going to,
hey James.
Yeah.
I just want to mention for the round to nearest that remap X is basically doing like what you did with renap number.
Oh, really?
If you didn't feel like using bounds and remap, you can just plug numbers directly in and then do remap X. It's basically doing the same. That's basically.
I see. Okay.
If you want it.
I see now. Yeah, I gotcha. Okay. Well, you can simplify things if you know your stuff. You can simplify things. We're going to take the vertices. And since they're triangles, right? Or can I look at one that isn't with a bunch of other ones? Right. You got this triangle here. 1, 2, 3 vertices. There's always going to be a 4th one to join it back, but we don't need that one. So we're going to do call index and take the vertices. We just don't need that last one. It's sort of like a duplicate of the first one, so that the curve can wrap around and close. We're going to set the index to -1, which just wraps it around to the last one. Basically, it's like, so you don't need to get the list length and then do like -1. You can just say -1, and it will remove that last vertex. So you'll see now all of these are, if I zoom in, that doesn't get bigger. All of these have n equals 3 vertices, and here they had n equals 4, which is like a duplicate of that first vertice, which we just don't need. I'm going to simplify this. This is getting a little long, right? Now it's nice, easy data tree. We're going to use a list item component to separate these vertices, okay? So take that in. The index should be 0. I'm not going to put a thing there. That's just the default value. And then we're going to use the in-circle component, and that's just a regular Grasshopper thing. Good. We're going to actually zoom in on the list item and get all 3 of those vertices, right? So you get the first one, second one, third one for each of these triangles now. And we're going to pop those in, boop, boop, boop. And now you've got these in circles of these triangles, which is like what we want. See, that looks good. And we're going to con plane, right? Construct plane. Oh, no, not that. We're going to, what is it? Plane from points or something like that. Plane. Got to go into this. Plane 3-point. That's what we need. So plane 3-point component. You can find it right there. Boop. It's right in the vectors in the plane thing. Plane 3-point. That's what we need. Not con plane. We're going to take this one into point B, this one into point C, and we're going to take the center of the circle. You can just do circles as points. Grasshopper will convert that for you. as the plane center. Right, so this is the origin point, this is the X direction, and this is the Y direction. I'm gonna take my display and change that point size down to 2. Is that good enough? Maybe 1. Yeah, that looks good. Because now we can kind of see the direction of things, right? Yes, looking good. And we're going to take the plane origin component. Wait, does this change anything? Don't need to do that. I don't know why I had that. Right, these are the planes that we're going to use. Don't need to do anything change there. And this will be the plane for the polygons. Oh, shoot. Don't plug that in, guys. I should have grafted. Whoops. I hope I don't have to quit. Oh, we'll give it about 10 seconds before I quit. I did just save recently, so that's fine. Oh, man, what a bummer. Yeah, we've got a bunch of planes. Oh, nice. Thank God. All right. Give it another 30 seconds for this thing to like double load. I hate when this happens. Classic. What we need to do is simplify and graph the nearest. Yep, just gotta wait for things to calm down here. Let me simplify and graft this. Whoops. This is why you save often, so that you can Control-Alt-Delete and quit without worrying. Gotta wait 30 seconds each time I change something. I hate this. Come on. Yeah, if you don't do this at least 5 times a day, you're not a real GH user. It's true. Come on. I should have just graphed it. I don't know why I simplified. Oh, man. All right, we're almost there, guys. Now it'll work. Thank God. Ah, there we go. Very good. So just make sure you grafted this. Yeah, I don't need to simplify if I'm grafting. What am I doing? Right. Very nice. This is what it should look like. 3 segments. We don't need to fill it radius on these. Let me hide these planes and circles so we can get a look at what we're doing. Also don't need to look at these points anymore. Unpreview all that. Look at all this stuff we've already built. Wow. Got a lot going on. Might as well save. Probably a good point after that close call. Almost had to quit there. Right, so you'll see now that things have been mapped by their distance. Wait, what am I still previewing? Don't need these. I'll keep the point, the attractor point out so we can move it around. You see now the faces based on their distance to the attractor point have taken one of the sizes of the whole typologies is what we called it, right? So these small ones are 0.25 radius. These medium ones are 0.5. And the closest ones are going to be 0.75. And that's good. You'll also see that each of these is aligned to one of the segments. Like one of the edges of these triangles is aligned to one of the edges of the face boundaries. And that's good. So they're not just like randomly rotated. Like one of the edges will always be parallel with another edge, as you see here. And that's just like kind of looks nice. So now that we
James,
see this,
you have a question.
Yeah.
Kind of a good question. Is the in-circle plane output the same as the plane you're making?
Oh, why don't we check that out? Maybe it is. No, it's not. So you'll see that if you do that, the no edges are going to be aligned. It's oriented incorrectly. And then when we eventually need to cut these and make tabs for them, like you fold a tab here and it will like hit this edge. So you don't want to use that.
It's oriented more like a subdivision.
Right. It's like the opposite. It's like from the vertices, the midpoints. Yeah, it is like a subdivision. So it's like the opposite of what we want. So that's why we create this 3-point plane, so that we make sure that one edge is aligned to one of the edges of the faces. And that'll just kind of guarantee, even if you have like a pretty wonky triangle, that it's like not going to be interfering with anything else. And if we go back now and change these biggest hole sizes, you could go like a little too large. Later on, what we're going to be doing, like I showed you with the petals picture here, these each are going to get like a tab folded. And so there's like the way they connect on the underside of these white faces, right? These red petals have tabs. So this is where we make sure we have enough room for that to happen. So you don't want something to be a little, this is like a little close to the edges here, a little too close maybe. So that's why we take it down to like 0.75. And I think maybe this could even be a little larger, maybe 0.3, 0.35, maybe the smallest hole size. Doesn't need to be minuscule. And you can see now what happens if I move the attractor point. You can see the triangles all moving. That looks cool. So we'll find a good spot for it. I kind of like it like up above, maybe like, yeah, up here. I liked it where it was, really. That's good. I think that looks pretty good. And you can always play with the borders, so you don't have any near it if you like that, or you can extend it further or less. I like, there looks pretty good. That's nice. Great. So I'm gonna hide this attractor point. Don't need to look at it anymore. We've got that good there. Oops, I gotta zoom in on my reference photo. I'm not just doing this all from memory. I do have the Grasshopper script already written in another window that I'm referencing. All right, next we're going to create the actual petals that will fit into the holes that we've got now. And maybe I will bake these triangles into the triangle holes thing. Yeah, yellow looks good. Right, so now we've got those. We're going to move to another layer. I'm going to lock this one so I don't accidentally move anything. And I don't need to look at those either. Right, great. So we've got that geometry baked, just like the mesh, so that everything is set in stone once you bake it, which is what we want at this point. We are going to generate the actual, the actual petal geometry that's going to slot into these holes. These will become holes. We will explode these polygons. Oop. I'm just putting some space between like each section, kind of. Right here, we're going to explode these. We're going to get the curve middle. You can use like an evaluate with 0.5. I just found out about this component. I've always just been doing eval with 0.5. Can you believe it? We're going to get these. We're going to get the distance. And the distance we're getting it from, I just got to follow this curve. Oh, it's going all the way back to that original point once again. Right. So the distance from the midpoints all the way back to this attractor point once again. Maybe I'll pop a little group on there and call this attractor so that we can find it easier. I really hate this long wire. I'm going to change that to faint. Yep, curve middle, distances between them. Great. We're going to now sort the segments by their distance to that. And this is so that the openings of these petals, I keep closing this picture, I should just leave it up. The openings of these petals, in this picture, they're just random, but we're going to orient them so they all kind of flow either away or towards the attractor point, so that they're all sort of in a cohesive direction. Right. We're going to get these as the keys. And the values are going to be these segments here. So we've got one distance for each midpoint of the segments. So we've got matching data trees here. We're going to get the list item component. And since there are 3 segments, we're going to pop open those 3 outputs from there. Index is going to stay at 0. Don't need to mess with that. Change this to this. We can unpreview that sort of thing. I think I'm going to, yes, we're going to join curves. Let's see, I think it's these 2. Oops, these 2. Right, so if I zoom in now, you can see that it's basically choosing the edge that is closest to the attractor point. So you see that like all of these are sort of facing this direction, facing like upwards now. The opening of these petals would be. The unselected line, the red line, is always closest to the attractor point. It tries to find the edge that is the closest one. I think I actually don't like that. I'm going to reverse it and have it be the opposite way. So the petals all face away from the attractor point. And you'll see what I mean when we get that geometry actually going. Grab a rotate axis component. This is from, oh, it's just a regular Grasshopper component. Good. Look at that data tree. It looks horrible. Let's simplify it. It's really just one anyways. We can graft this input. Not going to make that mistake again. We're going to get a panel, and the angle that we're going to use is -90 degrees, right? Oh, right-click this, change it to degrees. Radians are okay, but I'm a human, so I feel like I use degrees a lot more often. The list item that we didn't grab, right? We're going to simplify that. Oh, we don't even need to because we're going to graft this, whatever. Boop. Great, great, great. So what we've just done is we take the these 2 curves, right? And we rotate them around the unselected curve to get it like standing up, kind of like pitching a tent, sort of. We're going to, once again, explode. But this time to get the vertices. This item, 1, 2, 3 vertices. Quick save. Just, I saw my computer thinking for a second. It scared me. And now we're going to get the arc 3-point component. And this is where you'll see the thing taking shape, right? So you just plug these directly in. Boop, boop, boop. Nice. Look at that. I can hide these. This is what we're talking about here. Is this these arcs? We're going to do like a extrude to point type thing. Right. That's what we're going to do. We're going to get the extrude to point. Where's that? Here we go. The base is going to be this arc, obviously, but the points, we've got to get like this point here so that we get like a cone type shape, right? And all we got to do for that is come back to this original explode, get these vertices. We're going to put it into a goal index with that -1 once again, because we just don't need that last index, that last vertice, because there's a copy of the first vertice always. We're going to check the distance. You could do this a bunch of ways because we're just getting this point. So you could just like get it from the other curve, I guess. This is just how I did it. Check it once again against that attractor point. Yeah, this is probably not the smartest way to do this, I guess. I mean, it's not the computationally simplest one. This is just going all the way back to that attractor point, just like the other distance things. We're going to sort the list of these vertices by their distances. And this way we can get the one that's closest, which will be the point that we need for each one. Very nice. Look at that. There it is. And let's just make sure before I plug anything in that these look the same. I might as well simplify and simplify. Those look good. So let's do this. Wow. I love it when things work before we start looking at everything. Let's hide all that stuff. Okay, so now you've got these nice petals, is what we called them, and they're trying to look away from the attractor point. Maybe I should show the attractor point so we can see that effect, if that's working correctly. Right, there's the attractor point. So if I look at the attractor point, like down an edge, you should see the inside of like all of these, and we do. You know, they're not going to be perfectly facing away because they need to sort of go towards the closest edge that they can to do that. But looking up at this, you never see inside any of them. And if you look down from it, you'll see inside all of them. So all the petals are facing away from the attractor point. And that's what I like. That's the effect that I wanted. So that looks good. Oh, you know what? We can do like a, I was going to say custom preview, but don't need to see the holes anymore. And we can bake these to layer 4. Bake these to layer 4. We'll call this petals. And if I hide this now, maybe I'll, oh, see, look at this. So they're all inside out. So that's just like, that's why you got the color back faces on. So I'm going to select these objects and just flip them. Nice. And now they're all easy to tell what the inside versus the outside is. And you can see that when I like look down one of these branches, you see all the insides because they're all facing away from the attractor point. And this is like how you can see that, you know, the color back faces on, and that's in the display settings right here. Nice. I'm going to save my Rhino file because we've now got the environment, the skeleton, the mesh, the triangle holes, and the petals. And that's looking good for sure. I'll save this as well. Okay.
Before you go too far, there's a question if you can explain just quickly from like explode to list item to arc. You know, like if you want to, like the explode is just getting you the end
here,
vertices.
this one?
Yeah, like from there. And then
yeah, for sure. No problem. Yeah. Let me explode that. I'll hide the petals so that we don't get confused there. Maybe it's an earlier explode, probably this one, I would assume. So that's taking all these triangle holes, which we've just got, exploding them. We're going to get the midpoint on each of those, right? These points. And that way we can check which edge, which of these segments is furthest from the attractor point. That's what we're checking with this distance component. And we're going to sort that, and we're going to, if I hide these things, it becomes easier to explain. So you see then we get the 3 segments, and we choose 2 to join together. If I come here, you can see easier because there's none behind it. And since we did the sorting by distance, now the opening, right, the opening of the petals is going to be furthest from the, it's going to be on the segment that's furthest from the attractor point. Then we rotate this geometry about that, that segment, right? We rotate it so that it's in 3D, like upwards, spiky, right? And we use that to create an arc, right? An arc. And then we basically, you might be able to just like loft between these two, but what we did is we did an extrude to point. You might be able to just like loft between these arcs and these curves. And this comes right from the triangle hole curve where we explode it, get the segment that's furthest away, don't use that, and we use this instead. And then we just extrude to point there. And the way we do it is we just get that vertice. You could get this in a bunch of ways. I did it by checking the distance. And that's how you generate the petals. I hope that made it clear. All right, great. I see someone in the QA said, is there a way to optimize strip width? We're going to get to optimizing the strips in just a moment. That'll be the next thing we do. But this is basically where the form finding ends and the real fun begins. Let me hide this attractor point. Don't need to look at that anymore.
So it's probably a good point to give them a file soon.
Yeah, I'm gonna send them this file. But let's just take a nice look at everything all in one. right? You've got the triangle holes, and you'll notice that there's no holes actually cut into the mesh yet. That's why we have these curves. We're going to use those later to cut holes. But this is what you should have, and I will save these two files and open up Dropbox. My Gmail, Dropbox. Okay. Downloads. Right. I'm going to put them in the same folder, Mike.
Yeah, that worked.
Okay, great. Let me just make sure I'm getting the exact right ones. I don't want to do one that was from a while ago. Date 6/23. No, it's the wrong one. It's in here. 6/26. That's us. That's right now. Pop this in there. And I'll pop the 3DM in there as well. Right. So these are going to upload into Dropbox the current file and the current form finding file, which we are finished with now. We're going to now move into, after this, once we get these files to you, we're going to move into the strip making, I guess, and labeling and like fabrication readying portion of the thing. Okay, how do I send a link to these?
It's the same link, yeah. You put it in the same Dropbox.
I put it in the same Dropbox, yeah.
Yeah,
oh,
so
yeah.
I put it.
So it's the same link. Great.
Yeah, I put it there.
Maybe we can do like a 3-minute, 4-minute, 5-minute break right now. Seems like a good spot. So everybody,
let's do it.
Go to the bathroom, get a drink, get a sip of water, get a juice box. We'll be back in. It's 12:30 now. We'll be back at 12:35. Okay, 5 minutes.
Yep.
Cool. Okay, I see that some people asked some questions. I can answer them. Give it one more minute to people coming back. Can you go into more detail about how the plugins are creating the form and some technical terms that are associated with this type of form making? Sure. So basically, we start with the skeleton of lines, and using Fattener, or Daniel Piker's Fatten, this component here, that sort of turns it into a solid quad mesh with really nice topology. And then we're going to subdivide it so that it has a little bit more faces. And then we relax it with dynamic relaxation using Kangaroo. And that's how we get this like sort of form that looks like it's pulling on itself. Everything is in tension, basically, is how I would describe it. So those two plugins, I mean, Kangaroo is not really no longer a plugin. Fatten and Weaverbird, I mean, everyone should have Weaverbird. I don't know how you use Grasshopper without Weaverbird. Got to have that. And Weaverbird and Fatten both do that. MeshMachine then turns it from the quad mesh into this triangulated mesh, which is great for cutting into strips, and triangles are always planar. So for fabricating off of planar materials such as paper and a laser cutter, that's perfect for that. So those three plugins are definitely important to this. I use a few Pufferfish components here and there so far. I mean, Pufferfish is another really good one. We even are in the presence of the author. It's a good one. Everyone should have Pufferfish. I use it all the time, and it's just like, not even maybe for like its intended purposes, but I use all the miscellaneous components a lot. So it makes things like a little bit easier. And I think so far that's all the plugins that we've used. We are going to use a couple that are like really important pretty soon. So I hope that answered your question. Is there a way to figure out which library a component comes from? Yeah, you can hold Control and Alt and click the thing, hold click, and it will show you like exactly where that's from. See that? So you can then mouse over and know that that's either Kangaroo 2 or Kangaroo 1. All right, we're going to get back into it, though. I feel like I answered your things, hopefully. Answer done. All right. I hope everyone downloaded this 3DM file, because now we're going to move forward using that. We're going to start a new Grasshopper file. I just got to get my reference image up so I know which thing to go for. This is like how I am going to explain the whole thing to you. This is what we're going to make. Got a lot of components on the canvas there. Got a lot of grasshoppering to do. All right. We make sure you open up this Rhino file, and we're going to start a new Grasshopper file, because everything is baked. And that's why we did that, basically, so that everything is baked into the Rhino file. And notice I've got everything locked. I really don't want to accidentally move something like by clicking and dragging it. So I lock everything after I am finished with the layer. Right. Oh, here's where we're going to first grab some C# stuff. And this is fun. So we've got this back in the original downloaded file, the Syntactic Elements V1 all C# script components. We had the orient people to screen, but now we've got all these C# components, which I just do not want to do live, basically. We're going to grab that first one, which in the file is grouped as split mesh along edges. Get this component, copy it, paste it into this new Grasshopper file, and enable it. I'll briefly explain what this does once I set it up. So let's get a mesh component. Let's get a mesh component, and we're going to drop in, obviously, gotta unlock. We're going to drop in that mesh that we just baked, our mesh. That again. Don't need to look at it. I've already got it on the screen. Pop that into the mesh. Basically, the way this works is it's going to cut the mesh along edges. So we can like break this into manageable chunks for when we're doing the
James,
next
you're
sections.
getting some bifocals requests.
Oh, of course, it's a new one. I should have known. I forgot.
Don't forget to save.
Yeah, I know. I might as well do that literally right now. All right, everybody, save this one right away. We're gonna call this strip making. You could just call it everything else because it's gonna do everything else basically besides the form finding. Right. Got the mesh. Got this. We're going to now grab some curve component, which this is, we're going to do something inside of Rhino for this, and then plane component, which we're going to convert the curves from curves to planes. We're going to pop that into there. Basically, the way this works, I keep saying that, but I should just show you right away. I feel like showing you is easiest. We're going to take, back in Rhino, we're going to take a rectangle, and I like to just be on this last layer also. Take a rectangle component and, oops, I got to turn off some stuff. No more smart track. Draw a rectangle, and it doesn't like have to actually be around this, but it's easier visually if you have them like in space where they're going to be. So draw a rectangle like this. It could be on any of your branches if you're not making the exact same shape as me, and just like bring it up like this far. You know, like get this much of mesh in there. We're going to take this, set one curve there. Now we've got two meshes in this, and we're going to need to visualize that, right? So we got to get a list length component and a item index component because we're using a gradient. You can use whichever gradient. I'm going to use this rainbow because that lets me see like the most. Okay, we're going to grab a subtraction. Normally I would just do this in the expression part, but I want everyone to be able to see exactly what it is that we're doing. We just need to get the last index, and thus the list length is the total length, but the last index is going to be one less than that. So the last index is that. Lower limit is 0, that's fine. We're going to plug both of these, list and item, so that we get a list of the indexes, and we use that as the parameter. This is so that we can visualize these meshes. I do this a lot. We're going to use a custom preview. This is from Human, I think. Maybe not. I thought it was. We can plug this in and this there. That did work, but the colors are really close. So what we need to do now is once we add a couple more of these, things will look a little better. So basically we're trying to chop up the mesh into like manageable chunks right now. If I highlight these two, maybe it'll be a little clearer. Yes, so look at this. This is what this C# component does. It takes these curves, rectangles, and using planes, basically, it will cut the mesh along the edges, right? But it won't create any new faces. So it looks at each face center and gives it a reference for every plane that there is and says whether it's in front of or behind that plane. And then it divides the mesh into separate meshes based on that. And what we're doing here is really important because for the optimization steps that we're going to take later, if you tried to do it on the whole mesh at once, it would take a really long time. So you have to make sub-assemblies, basically. I think I even have an image showing that here. Yes, this is what we're doing right now. We're chopping it up into sub-assemblies so that it's manageable for the later steps that we're going to do. We don't need to do quite this many, but you want them to be of manageable sizes. And by that, I mean, for fabrication reasons, you want them to be manageable sizes, like so that you can actually reach inside and fit your arm through and clip the sub-assemblies together. You don't want it to be like longer than, say, 3 feet, you know, your wingspan. But also, you don't want too many triangles for the steps we're going to take with Grasshopper later, so it's not too heavy for the computation that we're going to be doing. Like if you did the whole mesh at once, it would A, be impossible to fabricate, and B, it would be quite slow. So that's what we're doing right now. So just chop it up, and we're going to find some good spots for these planes. And remember, since they're planes, I'll show you right now. Since they're planes, it like extends infinitely. So if I rotate this like this, you'll see it cuts through that too. If I rotate it so that it, yeah, here, look at that. You see this plane is causing it to chop it here along this edge, but also down here. So try not to do that. You don't want any unnecessary chops, you know what I mean? It's easiest to start with like the exterior branches first, I think, and then like make sure that none of them are touching or gonna get in the way of any other branches. Like, is this one gonna chop at here? Let's look at it from the front view, the right view. If I move it there, yeah, so it's gonna get it there. If I just raise it up a little, I can move it back. I can even rotate them a little too. Right, that looks pretty good. So everybody, I hope, is just doing this because it's sort of a long step. You do kind of have to make sure you get them all good. Let's grab these two at once. Maybe I'll be able to use them here. Right, rotate that. Bring it in. This one, rotate that. Bring it in. That looks pretty good. Nice. Maybe I'll hide the petals so you can see it better. There you go. So we're just chunking it up. Somebody asked if I can explain the gradient inputs. The lower limit is 0. We're going to use the index of all of these meshes. You see there's multiple meshes coming out of the C script component because this C script component splits the mesh. So we get a few meshes out. We're going to get the indexes of all of those meshes, just like a list. You could do this a few ways. And we're going to get the list length, the last index. So we go from the first index, 0, to the last index, 6. And you can see that all of these go from 0 to 6. And we're going to color them with the gradient, just so that you can see differences between the meshes. It's not like you don't need that. It's just for visualization. Now, let's come over to this side. That's good. Another one. That's good. I just like to update it as I go so I can make sure I'm not accidentally like chopping off a small piece from the plane extending. Yep, that's looking good. Okay, last branch, and then we'll work on the body, basically. I'll just copy this one, move it up, move it over. Nice. Be that big. Copy it again. And that looks good. I bet this one, no, I think it's probably okay. Let's just see. Yep, looking good. All right, now if we wanted to cut this middle up, it does look like you could get a plane along here, and along here. And I think that's what we're going to do. We'll start with this one. This is where things get a little 3D. So it's kind of hard to see. Get that right there. That doesn't look too bad. Let's update this and see what that looks like. Nice. Good clean cut. All right, grab this one, maybe Alt rotate somehow. Up. Gotta scale it because this is a big one. I know it gets a little hard to see. but you just gotta power through it. That looks like it's gonna be fine. Add these in. This component is really helpful, and feel free to try to understand the logic in it. The C# one that I'm talking about here. I've extended this to work with closed breps, closed meshes, et cetera, for like when you don't want this like infinitely expanding plane. Sometimes that gets really annoying. It works for this, good enough, but it can be really annoying. And we're gonna maybe cut it one more time. Like there. Go rotate that a little. Yeah, looks okay. Not the most exciting step, I know, but definitely necessary. Nice. We've got all these. I'm gonna internalize the rectangles so that I can delete them. I don't want to look at them. Nice. We've got this thing all chunked up into subassemblies, and you could definitely go a little better. Like this teal one we're looking at here is like definitely too big, and maybe this one is too. These interior ones could get cut like again and again, but that's okay. All right. Very good. Now we need to grab these meshes. This is all just for visualization, so just leave that up there. Grab a mesh component, and we're gonna now start working on like just one subassembly at a time. So just one of these chunks at a time. And we'll probably pick one of the exterior ones, like one of the end branch ones, just because those are sort of the easiest. We're going to get that, and we are going to get a list item component, because we only need to work on one of these at a time. Can segmentation be automated with an optimizer? Might be a little tough to put those things there, maybe with some like really smart k-means clustering of like the face centers into so many groups, and then like try to find borders between the groups and place planes. It seems like a hard problem. I've thought about it before. I don't think it's like so simple. I think it would be.
Yeah. I think you could probably automate it, but for something of this size, it would be kind of a waste of time.
Yeah.
Like if you were doing like 1,000 of these, then you
you would
want
have
consider.
to. Right. Yeah, that's true.
But
like this only has like 18 subassemblies or whatever, 16. Yeah, if you were going to do something with 3 digits, I would definitely try to figure out a different way to do this. Like I wouldn't even use planes. I would just like, group faces by k-means clustering or something like that.
Yeah, and it would have to accommodate like average human arm length or something.
Yeah, like you do like a sphere check for like a radius that is like so big or something. Yeah. There would be ways, but this is the way that we're doing it now. And it's kind of like the more by hand approach, I guess you could say. So we're gonna get a value list, and we're gonna call this sub assembly. And this way we can see which we're gonna get. There is, no, I'm not gonna do a value list. I'm gonna use a slider. Yeah, I'm gonna use a slider, and we're going to make it whole numbers, and it's gonna go from 0 to 15, because that's the indexes. There's 16 values. 0 to 15. I can turn this off. I'm actually even going to turn this off. We don't need to look at that nice rainbow color. So you see now I've got just one of these subassemblies here. And if I scroll through, you'll see it will grab each one in turn. So this way we can just pick one of these to work on and don't have to worry about the rest of it. And so like if you were doing this for fabrication, like a real installation like we did, you just like run the steps that are going to come after this on each subassembly. You could definitely automate that too. There's some tricky stuff because we do some like Galapagos type things, but there's ways to automate all that stuff. But we're not going to dig into that, I don't think. I mean, I'll talk about it, but like it's not really something that we'll be able to do. We're going to get a text component, this is going to be where we start the like identification process of these things. They all need to have like some IDs associated with them, so we know which things we're looking at. We're going to set the multiple texts, and we are going to put on caps lock and just type the alphabet, A, B, C, D, E. The alphabet in caps. Make sure it's in caps. We're going to have some other letters later, and it's sort of like a hierarchy of things. And so this is like the main thing is the subassembly. We'll have that in caps. We're going to grab another list item component and just change the list to this. So now we've got one mesh and one letter. And if we change these, you see this changes too. And that's exactly what we want. So basically, we've got like the mesh and its identifier, you can say. Maybe I'll leave this so that we can see what this looks like. Put it in the center. Make it big. Looks good. And that way we know. Text input is just the alphabet. This is so that we can identify each of these pieces later. So you see how it changes the letter and changes the mesh. Now we know that this is mesh K, this is mesh D, et cetera, et cetera. And that's just the reason for the mesh input. I mean, the text input. It's just the whole alphabet, A, B, C, D through Z. We're going to, if you want to visualize the whole thing, this is something I did. So I think maybe it's worth doing. We can grab the bounding box of all the meshes. Boop. Look at that. That kind of looks cool. There you go. Render that. You're done. We're going to grab those. We're going to get the volume so we can get the center of these boxes. Once again, get the item index from the meshes. Maybe I'll back this out a little. Once again, get those. We're going to get the list item. And this is so we can get all this text from these. So the list item goes to the text component as well, just like how we did here. And we're going to do a text tag. Location is at the centroids, and the text is that. That's nice. So now, like, look, we can see, oh, how horrible. Color, gotta change it. Oh, nice, and you can make it large. There you go. So now you can see, visualize like which subassembly is what. And this is helpful for when you are referring to this, like which subassembly is next to which. Helps inform maybe the assembly order of things. The way we built it was from the top down so that we could hang things off the walls and ceilings. So you probably want to start with like M, L, N, et cetera, et cetera. We also built the branches inwards, so we went like P to O. So it's good to have the text tags. This is just for visualization though. So I'm going to turn it off. We don't need to see it anymore. Just for you to have, so you can look at it. Those. One other thing I do want to check is the face normals. Like so many things, sometimes they get like flipped, and I hate that. So let's check the vector display. I like the vector display EX. Get the points from the centers and the normals. Make sure that all those vectors are pointing out. Yeah, if they're pointing inwards, the mesh is flipped, but it's not, so looks good. I'll just disable this. That's just like something that I don't know, you could check it with like a cross product against a vector made from a line that is like from the center of these things. But just a visual way to check that. We're going to go ahead, get a data dam, because you don't want to change things down the line. We're going to zoom in on that data dam and add another input. And we're going to change the first input to be called mesh, and the second input to be called identifier. There we go. And these two things go in. Remember, this is the letter, and this is the mesh that we have right there. That way we can pass that stuff along without having to like recalculate a billion things if we accidentally change something. Although honestly, really hate the way data dams work. All right, we've got to get the face polygons. We're gonna go to Weaverbird. Here we go. Extract face polylines, sorry. Weaverbird face polylines, that's what we need. You can pass that information along. Yep. Here's where we're gonna start with like the optimization step, basically. And this is really the reason why we wanted to break it into subassemblies, because this step that we're going to do next would take an extremely long time if we didn't break into subassemblies. We're going to go to the Fox. This is the most important component in the whole thing, besides maybe fatten right in the beginning. I don't know how you, there may be some other ways to do this, like some other plugins that do this, but this kind of thing is hard to do otherwise. What this component's going to do is it's going to cut the triangles into strips, basically. Like if I put that there. Yeah. Maybe I'll do a bang so we can get a quick preview. Maybe not. Whatever. This is the thing that's going to cut into strips. We don't really have the way to, we've got to connect this with Galapagos, and we've got to set up all the sort of fitness goals, basically. We're going to, if you've ever used Galapagos before, it's like a reverse. It's like you got to go backwards, basically. All right, here's what we're going to do. Get a list item here. Index. Yes, that's good. Oh, this is how we can visualize it. Oh, well. All right, on the Walker component, we've got true scale RX, RY, and L, J, I. Right, we're going to put a I is for iterations. We want it to do like 300 iterations per thing, per loop. So we'll set that to 300. And for the RX and RY, we're going to make, this is like a rotation in degrees in the X and Y direction. I think that's more like really UV and U and V directions on this mesh or something. We're going to make a slider from 0 to 180, because that's like all the degrees that we'll need. So 0 to 180. The Walker component is from Fox, which is the most important one to have pretty much at this point. You've got to have this one, Fox. It's really for like tiling stuff, but this component is like really good. We're not going to use any of the tiling stuff. We are going to use the Walker component. This will chop it into strips. We've got 0 to 180 on this slider. We're going to copy that. That will go into the RX. This will go into the RY. So that we've got two independent sliders for the rotation in X and rotation in Y. L, this is basically, since this is chopping this into strips, that's what this Walker component does. If you look at the mesh, you've got this face, this face, this face, and then this face. That could be a connected strip, right? And that would be a strip of length 4. 1, 2, 3, 4. Basically this L component, this L input is asking for the like target strip length, just like how MeshMachine has the target edge length. You know, not every strip is going to be perfect. We'll set it to like 4 or 5. You don't want to set it too high because if you think about it, there's going to be like some optimal number for the strip length to have them nest efficiently. Like if you have very long strips, it'll probably be hard to nest them efficiently later onto the material sheets for laser cutting. So you don't want to pick something too small either, because you don't want strips that are only 3 triangles long. So maybe we'll up this to 5, not 56. Whoa, up this to 5. Right. Now we've got to set up the stuff for the fitness that we're going to use with Galapagos. If you've never used Galapagos, what I just said is probably pretty confusing, but you will see shortly. We're going to go ahead and get a, first we need to make sure that the smallest strip is at least 2 long. We don't want any single triangle strips. And I say that with like air quotes, because it's not really a strip, right? It's just one face. This thing will accidentally produce those. We want to make sure that the shortest strip is guaranteed to be 2 long. So what we're going to do is sort the list. The P output is the list, the lengths of all the strips. I don't know what P stands for, and there's not really any helpful hover hints on these either. So I just know that P is the lengths of the strips that it outputs. So you'll see, if I zoom in on this, actually, sorry, this doesn't get larger, but the lowest number on this is 1. So we know there's at least 1 strip that is a single triangle long, which is not good at all. We're going to get the sort these lists, find the smallest one by getting the list item. Yep, and you see that if I hover over this 1, I'll put a big font panel right here so we can see what that number is visually. Don't need this like that. If we have that, now we'll know. We're going to get a number component, and we're going to pop in an expression on this, and that is x to the power of x. Don't worry, I'm going to label it x power of x. This is the expression that's inside this number component. The reason for this is we want to reward the fitness score when it's more than 1, and we want to reward it like exponentially greater. So if this was 2, if the shortest strip is 2, this number will be 4, which is like an added bonus. So if this is 1, it only gets 1, but if it's 2, it gets 4. So it's like 4 times as good, essentially. I can put this, connect to this one too. So you'll see the original number, the shortest strip length versus the like goal that it gets. Not only that, let's group this and say smallest strip there. Not only that, we want to increase the average strip length. That'll be another goal for our fitness value. So we'll get the average strip length, which is like 4.5 right now. And I will show us that. I like to see the numbers change as we go. Average strip length. All right, and now we're going to do addition of this number plus this number. The result is 5.5-ish. And then we're going to penalize. So all these positive numbers, right? We're like rewarding it by giving it a higher value. Higher is better, basically, for this fitness. We're trying to maximize the fitness. We're going to penalize it with a subtraction component. We're going to subtract from this number the list length, because we don't want, we also want to incentivize it to produce the fewest number of strips. We don't want to have a bunch of strips. We don't want the smallest strip to be 1. And we want the average strip to be high, the average strip length to be as high as possible. So these are the 3 goals, 2 good ones and 1 negative one, I guess you could call it. I don't really know the exact terms for this. If you are interested in Galapagos stuff, you should read It's like I eat bugs for breakfast, that blog spot. That one's really good. Okay, now we've got the subtraction result. It's okay that it's a negative number. Like that doesn't really matter. We're just going to try to improve upon this number. So remember, we're just basically getting all this data from the strip lengths. So we've got the smallest strip length, the average one, and we're trying to reduce the number of total strips to something sensible. Right. So let's get a num component, pop that into the end result here. This is where I'm going to use Silvereye, but you can use Galapagos exactly the same. All you do is plug the fitness into the number, and then the genomes are going to be these rotation in X and Y from the Walker component back here. That's the genomes. Yep, those are the genomes. And what this is going to do is, if you've never used Galapagos, it's going to move these sliders automatically until this number is the highest that it can be. So it's going to try to find the highest number, the highest value. But I'm not going to use Galapagos. I'm going to use Silvereye. Silvereye uses particle swarm optimization, which is instead of this like evolutionary optimization solver, this is a particle swarm optimization solver, which uses like similar techniques. So like similar values flock together, like how you might see in like you may have learned about like Boyd's or some other agent-based design methods. Silvereye basically uses that, but with numbers. So we want to maximize this value. Make sure that you set either in Galapagos or Silvereye, if you're using Silvereye, to maximize. Because if you do minimize, we'll never get anywhere. You know what? Sorry. First, we're going to want to be able to see what it's doing. So let's do a little visualization. I know this is like not very exciting stuff, but it'll all pay off once we get to see it change it by itself. It'll look really cool. We're going to get the mesh from polylines. Where does that come from? Also from Fox. Okay, so the mesh from polylines component, sorry, I'm not zoomed in. Mesh from polylines component, also from Fox. We're going to grab these from the list item right here. Grab these. We're going to do another gradient list thing. I can actually just grab this stuff right here. Just copy that over. Whoa. Copy that over. Whoa. All right, here we go. The geometry that we want to visualize. I'm gonna flatten this output. List length, list item, list index, just like we did for the other thing. If we enable that right now. Now you can see all the strips. Look at that. So this will visualize all the strips in a way that you can tell color-wise, like, you know, which is which. And this is nice to see. All right, now this will look cool when we hide all this stuff. All we need to see is this visualization, the rainbow visualizer. And we'll run Silvereye now. And remember, it's trying to make this number, which is the fitness score, as high as possible. So, you know, if it goes to -22, that's better than -27. It's a little weird with negative numbers, I know. And the way it's doing that is it's trying to make the smallest strip large. It's trying to make the average strip's length large, and it's trying to reduce the length of the strip list, meaning that there's fewer strips in total. This works exactly like Galapagos in that you can set it to maximize or minimize the fitness, and see how fitness is plugged into here. I'm going to set a runtime limit because this thing will go for a while. I'm just going to set it for 3 minutes. In Galapagos, it's kind of easier to stop it, but in Silvereye, it like freezes up the whole thing. So I've got it at 3 minutes, runtime limit. It's set to maximize. I'm going to do it. And you see these numbers are changing. That's because it is over there grabbing those sliders and moving them around. I should have showed that, but my canvas is now frozen, unfortunately. You can see it trying to figure out these things, and you'll see that when it says 2 and 4 over here, that means that the smallest strip is length 2. We may get a 3. Oh, I just saw one. That's really good. That'll probably be our biggest strip length. Our shortest strip length improves. All right, we got 3 minutes on the clock here while this thing goes. So let's see the Q&A. Can you share some resources about developable strips? I'd like to learn more about techniques and theory of them. You could probably go on to the Grasshopper forum and search Daniel Piker and developable strips and find a lot of good stuff. I know he's done some stuff. There is this design firm called Newhouse, PNEU House, and they do all inflatables, and they're in Providence, Rhode Island, and they do some stuff. I know they've developed some things for developable like surfaces, not like triangulated strips like this, but so that they can sew things together and inflate them. All right, great. Looks like the fitness value improved a ton. This is looking good. Our lowest, our shortest strip length is 3. So the smallest strip length is of 3. So like this really hot pink one, which you cannot see the outlines of, 1, 2, 3, that would be the smallest strip. There may be a few of size 3, but like this one, this green one here, also size 3, 1, 2, 3 triangles. That's great. A lot of times you won't be able to get 3. You'll only get 2, but it's not so bad. That looks good. Let's actually make sure that we are doing one that has some holes on it. Okay, so look at this. I'd like to, in the end, use a subassembly that like has a few of these holes on it, just so we can see how that works. So actually, we're gonna go back here and move this around until we get to one that has some triangle holes on it. There we go. This one looks pretty good, right? Got some holes. It's right on the edge, like that. So we'll move back, hit the data dam. Gonna have to maximize these. Oh, this time I will zoom out a little. And you'll be able to see these sliders moving as this thing does it. So we'll set it again for 3 minutes to maximize and start. Okay. So we said, would it be possible to optimize strips so their borders are as close as possible to parallel to a vector? Like draw a line through this segment and try to get strips that go along that segment in the direction the quad weft went in the earlier iteration. If your goal is to get strips that are aligned to the like warp weft sort of directions, you could definitely just like manually do that and like do a triangulation that is not random like this with MeshMachine. You could do like a, you know, if you generate those triangles in some way from the quads directly, you could probably control all the directions exactly. If you wanted to do it from random like this and use the Walker component where it generates these strips based on the rotation X, rotation Y, as long as you can express the value of that thing in a numerical value, if you can express the fitness value numerically, so like the parallelity to a vector, you get the dot product of that vector with the strip orientation, you could try it. And I think as long as you can express it numerically, you can use it as a fitness value. The studio that I mentioned doing inflatables is Newhouse, PNEUHAUS. I'm not choosing to do random orientations for structural purposes. The MeshMachine triangulation, it sort of, there's no directionality to it afterwards. Like it doesn't retain any of that information from the warp weft directions from the nice topology that we had in the quad mesh. The MeshMachine just turns it into triangles that have target edge lengths as close as possible to what you asked for. And then what we're doing here, the strips, we are optimizing for things other than the directionality. We're optimizing for smallest strip length, we're optimizing for the average strip length, and we're optimizing for the how many strips there are. So see this one, we didn't get as good as we did last time, but that's okay. 2 is good enough. That's really all you can ask for. The shortest strip is 2, and you can see there's one right here, is this dark blue. That's just 2 triangles, 1 strip. That's okay. 2 is good, 1 is bad, but 2 is fine. Triangle holes we can minimize now that we know that some triangles are going to be on some of these strips. That'll be good later. Right. now that we optimize this, it's like weird how like all this stuff is like in front of this, but then we go backwards and take the output here and make that mesh from it. And you'll see the if I hover over this, it's now got 41 meshes, and that is all of these strips. So this subassembly is going to be made up of 41 strips based on the optimization that we've just done. Okay, what's next? Oh yeah. So if I bake this, here's the issue. If I bake these meshes, bake, and I pull this over here, you can see that some of them are flipped. That's why also another good reason to have the backface colors on. Also, just going to do a quick save. Haven't done that in a little bit. You'll see that some of them are flipped, and that's just a result of the Walker component. Some of them get flipped. It's never going to be like a mix. Like you won't have like some faces flipped and some not. Just some strips are going to be flipped, and it's really annoying then to like figure out which ones are flipped in 3D space like that when they're not part of a whole. So what we're going to do next is we're going to try to fix that. We're going to ensure that there's no reversed strips, right? And the way we're going to do that is with the C# component. From here, it's going to be the second one, trim a brep with many polylines. So come back to the C# component definition and copy that, trim a brep with many polylines, and bring it in. Where'd that go? Over here. Right. I'm going to move this stuff just sort of down a little because this is like the main thing that we're working on. Right. We are going to enable this, and we're going to get, once again, the boundaries from here. These are all the strips, remember, not the subassembly itself. These are 41 strips making up this one thing. We're going to make boundary surfaces, and here's another good reason why you want to make sure you don't have too many triangles in your subassemblies. They're not too big because like using surfaces gets really slow. Brep join, whoops. Join, bang. And because it's in a data tree where it's like, there's so many faces per strip, right? They're not going to all join together. You're just going to get one brep that is each strip now. And we're going to take the curves that are these naked edges, right? What that's going to be is the edges of all the strips. If I unpreview this and unpreview these, what else is previewed? Yeah. You can see now I've got the curves coming from the naked edges output from the mesh from polylines. These are going to be the naked edges of the strips. And what that's going to help me do is I can now flatten these. Simplify that maybe. Trim a brep with many polylines. So we just want to make sure that we have these all as like the strips are exactly remade as breps. Let's bake these and make sure. Oops, what do we got here? Empty output. Time to do some thinking. Maybe these need to be flattened. All right, we'll come back to this in a moment. Let me just bake this and make sure that everything is flipped right side out. No, it's not. That's the purpose of this, and why it's not working is annoying. Maybe I graphed that. Oh, is that all I had to do? Let's see. Bake it, fingers crossed. No. Shoot. Sometimes you got to troubleshoot. This should be ensuring that there's no reverse strips, but why isn't it? Oh. Well, we'll come back. We'll come back. It's no problem. Just trying to troubleshoot a little. Sorry, guys. What should be happening is, I don't know. This should be working. Maybe also the tolerance to be a little less, I bet. 0.01. 0.1. Can't be. All right, we take in the polyline curves, and for each of the polylines, we change it to a polyline curve, yes. And then we split the breps with the polyline curves, and we get the breps out. Well, I'm a little confused by this. Don't know why it's not working. Was working yesterday. All right, I just have to say we'll come back to it. That's unfortunate. Not sure why that's going. Mesh flip, yeah, you can, I guess, but knowing like which ones are flipped is like kind of annoying, and we also want it to be as breps. We can try to do this, where we'll get the average of the polygon centers of the face boundaries, right? So we got all these points. We're gonna get the average point. Oops, these should be flattened. Get the one average point. All right, we're gonna do this on the fly. We're gonna make a debrep. Wait, is there a face normals thing? Really annoying. How do I do this? Get the, we can try to put vectors from each thing to this, and then check the vector against the normal of each of these faces, and decide whether to flip that way. It's unfortunate that this isn't working. Like I really don't know why it's not. This C# should have been working. Not working. Don't know why. All right, we're gonna do it on the fly. We're gonna get the mean. Going to vector 2 point. So vector from here to here. Yeah. Yeah. From here to here. All right, so we've got this vector pointing outwards. And what we can do now is get the normals. Let's check those. Right, look at this. So you can see that a lot of these normals are facing inwards. I think if we do a dot product, between these two vectors. Let's see what values we get. Right, okay, so we've got some negative ones, and I bet those are either the ones that are pointing in or pointing out. So all we have to do now is flip ones that are negative. See what I'm saying here? We checked the vectors from the center point outward, and we're going to check against the normals of the faces, and we're only going to flip the ones that are, we'll test whether it's the negative or the positive ones, but we'll do that. So we'll get a less than, sorry, smaller than, change the second number to 0. Yep, that's good. So if they're positive or not is now in here. And we're going to take, it's from these surfaces, from the base boundaries that we were trying earlier. These are still in the same data tree structure as this is. And we're going to do a dispatch. This will be the dispatch pattern. These are the list. Let's check that this worked. Oh, that's looking pretty good. Pretty good. Let me bake that and check it. Oh, I love it when it works. So all of these are flipped. Okay, now let's check list B. And all of these are not flipped. Guys, it worked. Whew, stressful moment. Things not going to plan. Okay, so now all we need to do is do a flip of these ones. Yep, we can merge these back together. Put these into the join breps. Now I guess we don't need this C# component. Doesn't work anyways. And let's bake this and hope things actually worked. Oh, look at that. What a relief. And the strips are still as strips, if we just did that. Okay, that was a little off the cuff, so I'll go over what I just did, if anyone missed it. It was supposed to be a little easier than that. From the mesh from polylines, remember some of those are flipped inside out. So what we do is we get the face centers and normals of those. We get the average center point here of all those face centers. I'll be a little zoomed in. Get the average center point here of all those face centers. We create a vector from it to all those face centers. So you know that that's pointing outwards, basically, the way that all the normals should be pointing. They should be like close to it. And we get the dot product of the actual normals versus this vector that we just created. And dot product basically measures the parallelity of two vectors, essentially. So if it's negative, it's not very parallel, or it's like opposite, kind of. And we use that information. If it's negative, it's going to be less than 0, right? So then we use that to dispatch the ones that need to be flipped, only flip the ones that need to be flipped, and then bring them back in. Woo! Sheesh. All right, we're good here. I'm just going to clean this up a little bit, and we'll move on to the next step there. Glad that got figured out. Basically, the C# component should have done that pretty much. So whatever. All right, nice. We're good there. So that ensures that there's no reversed strips. Why don't we just group this? Ensures no reversed strips. Great. So we know the purpose, basically, of that whole thing. All right. And now we want to make sure that we can label which edges of the subassembly are naked edges. So we're going to get the get points for every naked edge in the subassembly. Actually, I'm going to save. Quick save. Never hurt anyone. All right. We're going to get a point for every naked edge in the subassembly. Let me make sure I've got this right. Yes. Okay. We'll get the BREP edges. We'll get the naked edges with the curve middle. I'll zoom in a little bit. Sorry, guys. Curve midpoint on the naked edges. You'll see that it's getting the strips naked edges, right? So there's like points inside here that are not what you need. We're going to get the BREP closest point. Is this the right one? Yes. These are the points that we're going to want to do. Maybe I'll simplify that a little. Yep, simplify that. And the BREP that we want to get is each of these. Graphed it though. That's not right at all. What am I doing? Things aren't exactly working, but that's okay. Oh, yeah. Okay. Pop a BREP join here. This is what I have in my notes document, I guess. Does that work? No, it doesn't work. Well, it doesn't need to be perfect. All I need to do actually is this. Flatten. There should be one BREP. Yeah, duh. This was easier. You just need these points, right? So you just need to get the BREPs, all the strips, join them into one thing, and get the naked edge points by getting the curve middle for each of these. See that? And that's what we need. Okay. Right. Now what we're going to do is drop a curve component in. And this will be so that we can get the triangle holes geometry. We're going to drop all the triangle holes into this. Yep. Internalize that data so I can hide these. And, let's see. And what we're going to do now is get the triangles that are on this thing so that when we unroll these strips, those triangles come with it. Okay. So those are there. We're going to get them. We're going to debrep this once again. Debrep it. Get the area of the faces. Quick simplify. We're going to get the polygon centers. Basically, what we're going to do is check the distance between any of these to find out which triangles lay on the faces. Where am I? Here we go. Yep. So there's the centers of all these triangles. And we have the centers of all the faces. And we're just going to check basically the distances between these. So distance. Got to craft these. Yep. Quality within tolerance. That's what we're going to check now. Oops. That should be here. So we're going to check the distances and check it to against like 0. We want it to be as close as possible, but the tolerance is going to be 1. 1 is probably good enough. And that's like, so as long as the points are within 1 inch, We'll do a dispatch and see if we did that right. Dispatch pattern will be the equality, and the list is the triangle curves. Move this down so we can see what we're doing. Yep. Okay. And then we've got to get a shift paths component, because this is like sort of not the way that the data tree should be. Get it from there. Boom. And look at that. If I hide all this stuff, you can see that we've now got the triangle curves, triangle holes only on the faces that are, we don't have any of the ones that are out here, only on the ones that are touching the thing. That's good. And the data is like that. This will be in a group called match triangles correct. So this is taking in those triangle curves, and this is making sure they're only the ones that are on the thing. Good. The next part is where it gets fun. We're going to start unrolling these strips so that we can see what they're going to look like flattened for fabrication. Maybe this is a good time for me to check the question thing. Can you just use mesh flip? That was when I was trying to figure out the thing. It's not so simple. You got to dispatch exactly which ones are right, and that's why we use the vectors. Possible to keep updating the files, hard to download plugins and keep track on the same time. I don't know what you mean. Should have downloaded the plugins first. Save different results from Silvereye. There is no way to go back to the last result. You gotta bake those, I guess, if you wanted that to be there. I answered the random orientations. That's due to the topology. Talked about optimizing the strips so their borders are as close as possible to a parallel to a vector, if you can do that mathematically. The studio name is once again PNEUHAUS, Newhouse. All right. The next step, we are going to unroll polysurface. This is a pufferfish component. When we were doing this project, we tried a lot of different unroll brep and unroll polysurface components, and sometimes we would get some errors. Like we tried TT Toolbox is another plugin that has this, and it just didn't work as well. The Pufferfish one works pretty reliably. The second number is a 0. Sorry, I should have put that in. Oops. Yes. Okay. Second number in the equality is 0. So you basically are checking the distance between all the points and the centers of the triangles to decide which triangle is like on the face. So you want it to be as close as possible, aka 0, but you have a give or take of 1 inch, right? And that's just so that if there's some leeway with the placing of these triangles. Right. Well, let's get our, to prepare this unroll polysurface thing, let's get our XY plane, pop that in. Don't need to look at that. Let's get the poly surfaces, which are going to be back here. It's these ones. And we're going to graft that when we get it. Let's look down. Yes. Looks like a big mess right now, but that's where we want it to be. That's what we want it to look like, pretty much. That just ensures to me that maybe I'll pop a list item on there so you can see what I'm talking about the top view too. This is like where they come out after you unroll them. Oops, gotta rep join at the end because they all come out separately. Right. And I'll flatten that. If I do this, look, we've got our first strip here. I need to get rid of the grid. There we go. This is our strip number 1. And we've got strip number 2, et cetera, et cetera. So after you unroll them, this is where they show up basically in a big pile over here, which is kind of weird. Yes. All right, good. Now we're going to take also these curves, triangles, and unroll it with them. So if I get a geo unrolled curves, wow, look at that. The triangles are in there. Okay, now this is where the we may need to redo this because this isn't with the same data tree. This is just flat. I don't know if this is going to work. Let's see. I just put the flat list in there. All these other ones have the same matching data tree, basically. Wow, looks good. Cool. So you don't need to have matching data trees to unroll things on the edges, it looks like. We might find out later that that's not true. That's cool. I didn't know that. All right, so it looks like we've got, if I can now just get a list item, I'll show you like one strip that has naked edges, triangle holes, etc. Maybe not. Whatever. Well, if we do this, and then a list, you don't have to follow this. This is just me so I can show you. Yeah, look at that. This one strip is perfect, perfect example. It's got two naked edges as marked by these points, which we'll use that to do some stuff later so that we know that these are naked edges. And we've got the triangle holes that unrolled with it. And if I go into perspective view, that's all, oh boy, that's all flat 2D. So that's why we have all this like separate information. So these two dots will become like labels later. We'll be able to tell which edges are naked edges and thus don't join to any other strip. And these triangle holes now can be cut. We'll set these into the cut lines at the end of the file so that we can cut that hole. So we don't actually have to do like a surface split. You know, this information is all that's needed because if you're cutting it on a laser cutter or something, that's all you need really. Awesome. Let's get a list length. We're going to visualize all the strips, but we need to like space them out so they're not all just on top of each other, you know? Do I need to flatten this? We'll see. Get a series. This is just like a random number. I don't know, like 12. Oops. 12. Step. Count. Unit X. We're just going to set like a move thing so we can move all these geometries. Yep. Space them out. Gotta graph this. And I did need to flatten this. Don't need to graph this. Or do I? That's what I should have plugged it into. Sorry, not the prep join. Yeah, let's clean this up a little. What we just did is we made a series of numbers based on the list length so that we can move each one in the unit X direction this many units, just so that we can space them all out. I'll move these up here just for a sec. Join these preps. Right, this is the actual stuff that we need to see. Don't need this anymore. So look at this. Now you can see all our strips like laid out in a nice row. And visual inspect, so some of them overlap. So I'll increase this, well, say 20. I just don't want any of them to overlap. It won't affect anything. It just, I just like want to be able to visually inspect them all. Right, so you see our smallest strips are just 2 triangles long. And our longest ones are probably around 5 or 6. And these are all the strips that are going to be a part of this subassembly. And now that we've moved all the strips, let's also move all the naked edge point labels and all the curves as well. So let's get another geometry and another geometry for the row curves. Let me delete these, delete these. So this is the naked edge points. This is the naked edge curves. And we've got all 3 of our things nicely. So we can now look at all of our parts. And no, not all of them have triangle holes. We saw that in 3D. Not all of them have naked edges either. But this is a good way. So now we've got all this information where we need it for all of our processing that we're going to do now. Woo! Nice. Glad that all worked. That stuff can be kind of annoying if you don't get it right. All right. So we take these breps. These are still the strips with their separate faces. So we join them. And we don't need to flatten this. Not to flatten. I will simplify it, though. Yep. So we've got 41 breps now. That's good. I'll show you them here. That's the same ones. What are we doing next is going to have tabs on these strips, right? The regular outlines won't do. We need to have tabs so that we can connect them to each other. Let me show you here what I'm talking about. This is what we're going to build right now. These tabs, the dashed lines that you see are the outlines that you're looking at right now that we have. We're going to generate these tabs. And we're also going to generate the labels, but that comes after. First, we got to have the tabs. Maybe good time to save. Save both your files. All right, so we got to get the wrap edges. Join curves to get those naked edges. Got these now, highlighted in green, just the naked edges. We're going to use these to create tabs. This is going to be a pretty big section, but that's okay. I'm sure there's like some plugins that just like automatically take an outline like this and generate tabs for you. But we can do it ourselves. It's not so bad. I'll even turn the preview off, and now you can see better what these outlines are like. And there's no interior lines yet. Right. We are going to, I know it's funny, I just flattened that. I'm going to graft it. It's because I flattened it because we're going to need it flattened somewhere else. Wait, no, I don't. I'm looking at my notes right now. Don't need it to be flattened. Simplify and graft. That looks good. We are going to actually hop into the C# script thing once again to get the polyline orientation component. This is the third one of the C# stuff. Get the polyline orientation because offsetting will be different depending on the direction of the polylines. When I paste it, I know it's going to come in way over here. Let's drag it back over. I'll show you what I'm talking about. You guys don't have this component. Display. This is a component that I wrote. Explode. If I explode the curves, plug the vectors in, you'll see that these ones are going counterclockwise. And this one's going clockwise. So some of these are flipped differently. You do have this component. It's the C# one right here, basically. I just didn't compile this one for you. I mean, this one has also the winding vectors. This one just tells you the orientation. Like, see, the orientation of the polyline is either -1 for clockwise, 0 for undefined, or 1 is counterclockwise. This is just like a compiled version of this C# component. Flip curve does work. That's what we're going to do. We just have to find out which ones need to be flipped. It's the same thing as the last time. You just have to know which ones to flip. So some of them are going clockwise and some of them are going counterclockwise. And that matters because when we do offset, and we're going to use Clipper, I'm pretty sure. Nope, not using Clipper. Clipper is just like the best offsetting thing, but I'll show you with regular curves. If we just were to offset these, see how some of them go outward and some of them go inward. And that's because some of them are different orientation. It thinks the curve is like facing upwards or facing downwards. And for some reason, that changes the way that you're offsetting, right? And we obviously want to offset outwards to create the tabs. So the reason we need to get the polyline orientation is that. So we've got the curves. Got the curves here. We are going to pop them into this. And for the plane, we just need the XY plane. This will tell us the orientation. So you see 1 is clockwise, -1 is counterclockwise. And we can use this larger than. And we check it against 0. So I'm not going to put a thing there because it's the default value. And then we use that to dispatch. And this will tell us which curves to flip or not. And we're going to dispatch the original list. Dispatch pattern is this. Let's just check. Quick geometry component. Yep. So this one, remember this was offsetting inwards, is telling me that I need to flip that. So list B is the ones that we need to flip. Curve. Boop. Actually, let me just make sure that's right. Offset curve. I'll merge these. It's either going to be list A or list B. You know, we'll just check it out, figure it out. Offset. Nice. So it was list B. So now everything is offsetting outwards, which is exactly what we wanted. Perfect. Great. OK. So all you have to do is you got to fix those orientations. Some of them are just not going to be the right direction, and it's kind of annoying, but oh well. What comes next is we are going to get the curve middles of these. We're going to move them and create the tabs. Basically, we're going to like rejoin and create the tabs. So here we go. First things first, another explode. I'm constantly exploding and joining things, but it's just how you do it. Get the curve middle on these segments. Just simplify. Keep it simple. We gotta get the end points. We're gonna make these tabs by hand. Back to point. We're gonna get the start and end swapped like that. Unitize is set to false by default. Gonna leave it as false by default. Get a z vector. What we're going to do is check the cross product. Cross product. If you don't know what this is, probably can simplify a lot of your Grasshopper definitions if you understand like vector math. Once I started using vector math, like it really like improved my Grasshopper skills. So I really recommend everyone learning about cross products, dot products, the right-hand rule, et cetera, et cetera. All right. So now we've got some vectors here. You can't see them yet. We're going to get the amplitude. Pop that in. What's the tab length that we want? We want something from 0 to 1, but probably more likely like just like a 1/4 of an inch. I'm going to label this slider tab length. Amplitude. Actually, I'm gonna put a toggle, and we are going to unitize the cross product. Okay. Do unitize the cross product. Don't need to unitize this because we're going to unitize it later. My favorite vector math resource is Jose Del Castillo. Oh man, I'm going to ruin his name. He does Parametric Camp on YouTube, and all the GSD 6338 course is like extremely good. Plus, it uses Grasshopper and C#. It's really good if you're trying to learn C# and Grasshopper. That is, look up GSD 6338 on YouTube.
We have him as a resource on our website, also resource page to that series.
He's great, and that series is like excellent. Really helped me learn some C# stuff for Grasshopper when I was like just learning. It really helped a lot. It's like the best resource for vector math too, because he goes really in depth on it all. Okay, now that we've got that, we can visualize these vectors, right? So we'll do a vec display just so we can see like what it is that we're doing. From the curve midpoints, check that data tree, check this data tree. Yes, they match. That looks good. So all these vectors are pointing inwards, and they're all going to point inwards because we flipped the curves that need to be flipped, right? So all these are going to be unified. They're all pointing inwards. And what we need to do is reverse them. We want it to point outwards, so I'll just put a negative component here. Flip them. That's good. So now all these are a 0.25 length vector from the midpoint of each of these lines. And we're going to use that to move the lines. We're going to go back to this explode component, which gets all the segments. And we're going to get an extend component. The segments are the curves that we want to extend. The type is set to 0 for line. That's exactly what we want, so I'm not going to change that. Yeah, I'm not going to change that. We're going to set the tab offset length, basically, on the start and end. We're going to change both of these to, I guess I'll just do it here. It's easier. Negative, right? We want to shorten these curves. You'll see in a moment like why and what I'm talking about. This is not tab length. This is tab width offset, perhaps you could call it. And we're going to get a move. And this is what we're going to use to move these. Oops, I did that backwards. Huh. There we go. Yeah. So you'll see now if I change this larger, these shrink in and out from the ends. And that's what we're going to use to make like the, you know, like you have like trapezoidal looking tabs, you know? So we'll set that as like 0.25 inward offset. And now we've got all these. And with that, we can take another extend curve. Is that right? Oh, yeah. Mm-hmm. This is the tab base width offset, which I'm going to set to 0. And then this one is going to be the one where it's the tab end width offset. Oops, what did I just do? Because sometimes you may want the tabs to like start sort of inward from here on the baseline and then go in. You'll see what I'm talking about. Put these on. Whoops, there it is. Right, same result. You'll see in a moment why it's good to have the two options. So we have the tab base width offset and the tab end width offset is what I would call this, I guess. You have the tab base, which is this line. You'd have the tab end, which is the line that we're going to join it to now. We are going to loft between, and we're going to get the curve component here from the base tabs, right? That's these lines that we didn't extend at all, or de-extend, whichever. We're going to graft this. We're going to graft this. And we're going to loft them. Look at that. Look at all these tabs. And now I'll show you what I'm talking about if you want the base width inward. So you can have tabs that are like this, where it doesn't extend all the way to the edges. That's just an option that you have now. That's the base width offset. I'm going to leave it at 0 because I don't want that. But if you do, some materials for like the thickness, accounting for thickness. And this is the tab end width offset. You see how it changes these trapezoid shapes, right? You definitely don't want it to be 0 because then things will overlap like this. 0.25 is fine. You also might see things that do overlap like that. I don't see any yet, but there might be some like corners where they do overlap. It's actually okay. We're going to figure that out later. Here, this corner right here, don't worry. Like you don't have to change this value so that all of them are always like this. We will take care of corners that go like this. So nothing to worry about. That's fine. Let's hide all this stuff. Don't need to see those vectors. Don't need to see those midpoints. Don't need to see any of that. Great. Let's turn these lofts into curves because that's all we need. Grab edges. Naked edges, obviously, that's what we want. Join those. Boop. That's good. And now what we're going to do is simplify. And you see that our tree is a little messed up right now. We're going to use the trim tree component with a depth of 1, which is the default value. Trim tree component is right there in sets trees. Trim tree with a depth of 1. And now it's back to our normal data tree structure where it's just like a single depth data tree with 40 branches. And that's how we want that data to be, because we're going to go way back. Way back here. Let me make a little separation. Sorry, just going to move things. Yep, we're going to go way back and get these original curves in green again. And we're going to put that in a curve component just so I can bring that over here. And they've been graphed already. We're going to bring that way far. We're going to merge this data, aka these outlines, and this data. Yep, and they're of the same data tree structure, so should look good. Yep, that's what I wanted. So now I can hide, come back here and hide this. No, don't need to look at the plane either. You can hide that. Right, things are getting a little complicated. That's okay. Once we got that, we're going to do a region union. And that's why we don't have to worry about this. These things will just fix themselves, basically. I'll get an XY plane. Sometimes things are a little bit more accurate, especially the offset component, if you do put in a plane for some reason. So looking at this and hiding these, you can see now our outlines are of the joined regions of the tabs, right? And that's what we want to see. That all looks good. We come back to the front here. Yep, all the tabs as one union region. And we are going to load it right away. Simplify, explode. Let's get a flattened tree component. We're going to need that from this output for later. The vertices, we're going to simplify that. Okay, now we're gonna take care of the ones that got connected, like I just said. Which one was it? Like maybe this one? No. Try to find one that got merged together. Here. Right here, it doesn't have a split for the tab on this one. It got merged together. What we're going to do is we're going to fix that. So we are going to go back into the C# thing and get the one that says for splitting tabs that got merged together. That one right here, that is going to basically check all the vertices. And if there's one where it's missing a vertice, like it should have had an extra one because the tab got split, it's going to put a line there. Let me paste that in. Gets put all the way on the left. Bring that all the way over. Enable it. Basically, it will draw a line from the original vertices that aren't in the offset vertices to the closest offset vertice. And the way this is going to work is we put the new vertices into the new vert thing, and the OG verts input, or original verts input, we are going to take from, let me find it, this explode, which is these original vertices. So see, it's these original outline vertices and the new vertices, and we're going to see if it doesn't match, we will move it to the nearest one. Okay, so let me make a point just so I can bring it down without it crossing over everything. Check that data tree structure. It's just a flat one, basically. Let me bring this over, make sure that this one's also the same type of data tree. Yes, it is. Look at that. That looks great. Let me hide this so we can see what we just did. Yep. So this component adds in the lines where the tabs need to be resplit after they got merged from the region union. It does that by looking at all the vertices. And if the vertice isn't in the original list anymore, it draws a line to the closest one. There's probably a smarter way you can do this. This is just like how we did it, basically. But you could probably do this a little bit smarter than I did. All right. Now we are pretty much done with that. I'm going to group all this into one thing. Let me turn this off. Yep. Group all of this into one thing that's going to be called making the tabs. Yep. Making the tabs. Huge group. That's what we're doing. This is the flattening. Let me just make this a group, the unrolling. Unrolling strips, naked edge, labels, and triangle holes. That's what this unroll polysurface group is doing. Quick saves. Do a couple saves. All right. And we'll come back to these points and triangle holes later. We're still working with the strips. Right. So these lines are basically like what you're going to cut on like a laser cutter or something, you know? And now what we can do is nest these curves on our material sheets. So assuming you're laser cutting paper, this would be like your sheets of Bristol paper that go into the laser bed to get cut. We obviously don't want to have to do this by hand, like drag each of these shapes into a little rectangle. That's why we're going to use OpenNest, which is an excellent plugin. OpenNest. Sorry, gotta zoom it in. Yep. All right, there's OpenNest. We got a lot of stuff we need to prepare for it. Not a lot. Not too much. We need to make a rectangle to be our sheet size. That like represents our sheet size. Right now, this rectangle is only 2 inches by 4 inches. Pretty common Bristol paper size. If you're cutting this out of Bristol paper, is like 24 by 18 for a large sheet. So we'll say the X is 24. If you put in just one like this to a domain, it'll assume it's 0 to that number. So that's how we're going to do it. And we'll change this one to 18. And now we've got a rectangle that's, let's say it's our Bristol paper size, right? You could plug this into the sheets, but it's actually a little better if you offset it first, and you offset it negative, like ½ inch, just so you give some room for these parts on the edge of the thing. So now no part will be placed within this margin. So you'll have a little bit of a room for things. Turn that there. And in the sheets, we can copy this back, take that, and put it to 0.5. And this way, it'll resize it to the normal size so we can see our sheets the right way. Okay, there's our sheets taken care of. For spacing, this is like the distance between the parts. We don't need 1 inch of space between the parts. I'll do like 0.125. Yeah, 0.125 spacing will be fine. Part spacing. This is like when you nest them together, how far apart they are from each other. Okay, placement, we're just going to leave at the same value. Tolerance, let's make a value list, because this one can kind of be annoying. We'll change it to 1, 0.1, 0.01, 0.001. That's probably it. We'll change it to 0.1. I think that's fine for tolerance. Yes. Rotations is on 4. I'm going to put it on 180. This is basically how, if it's on 4, it means it can rotate it in 90-degree increments, right? So it's like 360 divided by this number, okay? So 4 degrees of freedom versus 180. So now the angles can be quite good when it's trying to rotate these things to place them on the part, on the thing. Iterations is 1. That's good. Seed 1. All right. Now we need a toggle, and we need a button, just like with the Kangaroo solver. Button on reset. Toggle on run. And the last thing we need to do is save, because this can really crash your thing if you get the tolerance wrong. If you set the tolerance like really high, it will take forever to figure this out, really. The geometry that we are going to be nesting is all these outlines, right, that we got from the region union, all these outlines. We're going to pop that in. It's going to freeze for a moment. I can unpreview these. I'm going to come back and unpreview these two things too, the points and the points in the triangle hole curves. We just don't need to look at any of that stuff anymore, so that we can see what we've done here. And I can unpreview that, unpreview this. Geometry into the geo, just so we can see what we've done. All right, so now look at this. We've got our stuff nested onto the sheets, pretty blank though, but that's okay. We're going to use this transform output like extremely liberally. We are going to use the transform output a ton. And that basically, that data is like from where it took these curves and where it moved them to onto the sheets. That is the transform data, all that translation and rotation data. We're going to use that to bring like the triangle holes and these little tab split things, which didn't come along when we nested them. We're going to use the transform output to do all of that. Let me group this, and I'll call this nesting curves, nesting strips, efficient cutting. Good. All right. And this is also why I said we should make our little environment thing in the negative XY, because now all this stuff shows up here, and I just don't feel like moving it all. So that's, I mean, it's not too hard, but it's whatever. Okay. Once we've got that, we are going to create the tab fold lines. Yes, we're going to use the tab fold lines. That's the first thing we're going to use to get from the transform output. So we're going to grab a transform right here, transform, plug it in, and we're going to graft it. So from the transform output of the OpenNest to this transform component, we're going to graft that. And we are going to get the original outlines of the strips. I'm just following this long, long wire way back. Okay. This geometry input is going to come from this extend curve where the tab base width offset. Let me think about that for a second. Tab fold lines from this? No. Tab fold lines should be, oh yes, they should. Sorry, thinking out loud. Yep, and the reason for that is if you wanted to input, oops, gotta let it do that thing. If you wanted to offset inward on this, now these fold lines don't extend past here, and you can change this to a cut line, right? So it is actually better to have it come out of the extend curve output from the tab base width offset. Right, good. I'm gonna display this as faint because I hate it when there's like long wires that go across everything, making it hard to see everything. And now look at this. We've got our tab lines, which are just these outer lines, and we've got our fold lines for the tabs, which are these. And you could like change the laser setting for these two types of lines to be like, you know, this is a score and this is a cut through line. But I think it's a little better, and we did try a lot. I think it's a little better if you do it with dashed lines instead. So that's what we're going to do. So first things first, we get those. We're going to need to get another thing, but it's not these same lines. We need to get the from the region union right here. That's these same ones. I know that we have that here too, but it's just easier if we just use everything from the transform, so it's everything is the same. We can basically just ignore this now from the geo output. It is what we nested here, but I'm just using it from the transform thing anyways. That's just the way that everything comes from the transform, you know, and that's how you can think of everything. Now that we've got these regions, we're going to trim with regions. And I know that nothing is sticking out right now, but you might sometimes have something stick out. So we're going to grab these lines, curves, trim with these regions. We're going to get curve inside. It's the same lines. It's just a check, basically, because you may not always have that. You know, this didn't do anything, but that's okay. We're going to get the length of these lines twice. We're going to use it for different things. You don't really need to do it twice, but whatever. Vision. This is we're gonna turn into dashed lines right now, basically. So that's why we're getting these like weird stuff. We're dividing things. It's just so that we can make sure that we have a ratio for these dash patterns that like always lines up with the corners of things, essentially. So we will divide these lengths. First, let's get a slider, and we'll go from 1, maybe 0 to like 40. Just put that in there. We're going to double click inside it. This is important. And the ratio that we want to put on this slider is x times 3 plus 1. And this way, every number that comes out of it is a multiple of 3. You see what I mean? Oh, I don't need it to be so high. I forgot. Set that to 12 or something like that. So it can be 1, it can be 4, it can be 7. So it's a multiple of 3 plus 1. And this will be important for the dash pattern. I just find that this ratio or expression always results in things meeting at the corners. So we'll call this 3n dashed line ratio. 3n meaning the, maybe I'll do 3n plus 1 dash lines ratio. So you know what's going on with this component here. And that will be dividing the lengths. And it will be divided by 2 here. And that's going to be further divided by this to this. We'll merge because you need to make the gaps and the dashes. So that's why you have to have like these two things going. That looks good. Pattern, bang. If I hide all this, now you can see our dashed lines in here. And you'll see that as I change this, it always stays at the corners of the things. That's the magic of that ratio, 3n plus 1. You'll always get it nicely on the edges. So that looks pretty good for here. Yeah, that looks good. So that'll be like your cut fold lines. So now you can leave these dashed lines on the same layer as the outlines. And you don't need to worry about like etching and if your material will like peel between layers if you only cut through some of the material, like certain papers will. Dashed lines work for bidirectional folding and they don't peel. So it's just better. Also, I think it's a little stronger because then you have like areas of full paper. So if there's a lot of like pulling on these tabs, a score might start to rip and then like rip along the whole thing. But if one of these tabs rips, it may stop, you know, at one, or there's also just solid paper between each of the cuts. Right? And they just fold both ways. Dash lines are a lot better in many ways. They also look cooler, I think. Scores can be really ugly because you can get like laser burns and stuff. A whole bunch of reasons. Okay, so this was getting the tab fold lines. So let's put that into a group. Tab fold lines. Nice. All right, good. Let's get, we've already got some stuff here that we can start to organize into like our final cuttings. So I'm gonna just make 3 curve components. 1, 2, 3. These are gonna each get labeled the way I like to label, which is like a round circle. I'm gonna label this cut fold lines. And remember our fold lines are dashed, so they're still cut lines. This one I'm gonna label cut outlines and holes, because that's what we're going to put into this one. And this last one is going to be text. And this is just a good way for us to organize it for the laser cutter or whichever fabrication process you're doing. Etch. So that you can like put them on different colors or however the system works that you're doing. Right, that looks good. I'm gonna group these all together, put them out here, because we're going to have a lot of room to work with. Let me align centered. That looks nice. And we'll get some line weights, custom preview line weights. This is definitely from human. Yes. We'll get some swatches. This will just be so that we can tell which things are on what layer, like the fold lines, outlines, and the text lines. Maybe we'll turn this to be, I like the fold lines to be blue, the cut lines to be red, like the outline cut lines, and the text can be green. I feel like those colors feel like those things to me. Right. These aren't previewing anything yet, but they will be right now once I take this. Hang on, just checking, just checking. Yep. So these are all, this is cut fold lines. I can minimize that, and now we got it nice and blue on these cut fold lines. Red for the outlines here. Unpreview that, that looks good. This is the outlines, which we just plugged into here. Maybe I will move things, give things a little bit more room. Great. Okay, so I can hide these three. We're going to rely on the custom preview line weights now. I'm going to save again. Definitely save again. Things are looking good. Everything's nested. And now we're just going to start using the transform to bring everything else that we need, all the information that we need into the place onto the sheets. What geometry did I connect to the transform components? Oh, man. This one goes all the way back to the extend curve, the tab base width, which is these lines, the initial outlines that now become the dashed lines, basically. And this second transform is just from the region union. It's just like the outer tab outlines. See how they're chunky? Those are the tab outlines. It's what became the red and what became the blue. Okay, now we got those outlines there. Simple enough to get these tab split ones. We're going to need those too, like this line right here that's missing. That's easy enough. So let's get another transform component, change it to this. Did that work? Yes, it did. That can get grouped right in with the cut outlines and holes. And now we've got this tab. We'll split again when you cut it on the laser cutter. No problem. That one, once again, same transform output, obviously. And it comes from this C# component where we generated those lines, where it splits the tabs that got merged together. Maybe I'll start labeling these ones. This was the original outlines from the original outlines. This was from the region union. And this is from the tab split C#. Okay, great. So now it's kind of, you can tell where they come from. I know it's annoying with bifocals to like read these groups, but you can still do it. It's not that bad. All right, things are looking organized and good. Next, we're going to get the triangle holes, which is also pretty easy to get. We got the outlines, we got the, yep, let's get the, oh, you know what? Let's get the interior fold lines. So all the lines that go like from here to here to here to here to here, etc. Let's get those. That we should do. We're gonna have to reach far back for that. I'm gonna actually move these down because this next one will go into the cut fold lines area. I don't want to be like crossing wires, so it'll go here. We'll put that, what we're going to do right around here. Let's get under the transform component. This is going to go way back to the, I'm just scrolling to my notes. We're going way back to the unrolled and moved reps, right from the poly surface unroll. We're going to take this one and we're going to go way back here. Here we are from there. Let's check that I did that right. Don't worry, I will show you. That looks pretty good. These aren't joined. That's what we want, right? No. Okay, I'm going to move this back so you can see what I'm plugging it into, basically. This is that transform component. We're going to plug it into the joined brep output. Boop, just like that. Looks the same, but the difference is we can now debrep and get just the interior lines a little easier. Move that back. I'll label this with what I got it from. Joined reps. Yep. We're going to debrep so we can get those. Oh, not debrep. We're going to get brep edges. So we can get those interior lines only, like these lines only. Exactly what we need. We're going to make sure that we do the trim with region check again. I know it seems weird, but sometimes you get things that are not where you think they are, and that sucks. Here, same region is fine. That's good. Unpreview. Curve, just so we can see that we got the right things. Yes. So all these green lines we're about to add, that's perfect. And we can just copy this logic from here, the dashed line stuff. And we'll pop that into the fold lines and see if we did it right. Look at that. That looks great. And this allows you now to sort of have a different ratio for like the interior fold lines versus the exterior fold lines. Or you could keep these as scores. I don't know. It depends what you want to do. But now you have like control independently over these two things. I'll keep them at around 31. That looks good to me. Wow, look at that. So you could basically cut these right now and like fold them up, but you'd have a really hard time figuring out which ones go to which. I'm going to save. And I'm going to group these as well. Group these and call it interior fold lines. Yes. Great. What we're going to do now, is there a way to put a color to know the direction of the fold? Yeah, you'd have to reference like the angle on the original brep, but like I'm sure you could figure out a way to do that. You could put points only on convex edges, and then you could say, okay, if it has a point on the edge, then it folds this way, and if it doesn't, it folds concave, and you could dispatch it in that manner. That's probably the way I would do it. It's the first thing that came to mind. Get the convex or concave edges and put a point on it so that you unroll it with that point, and then whether it has a point on the edge or not, it gets colored differently. For a mountain or valley fold, I think that's what people call them in like origami. Right, now we're going to get the triangle holes. That'll be what we do now. Can move these up a little.
Hey James,
Yeah.
Just if you feel like maybe it's good to take another 5 minutes at some point when you feel it's good to stop.
Sure thing. Yeah. Yeah, we just came to a pretty good spot. Yeah, we can take a break. Yeah, we'll take a 5-minute break. Can we do a 10-minute break? Eat some lunch.
I mean, it's up to you. It depends how much more stuff you.
Well, we still have all the labeling and stuff. There's still a okay amount, like probably another hour and a half.
Yeah.
Let's take a 10-minute break, okay? It's 2:40 where I am, so we'll come back at the 50-minute mark.
Cool. Do you want to maybe just toss this file in?
As far as it is now, yeah, sure.
Yeah, just like whatever.
We haven't changed anything in the 3DM file, in the Rhino file, so I'll just pop this into the downloads folder then. Yeah, sure.
Cool. So 10-minute break.
Yep. 10-minute break. And I just uploaded it, okay?
Sweet.
All right, I'm gonna go eat something really quick. Bye, guys. Did the file get uploaded? Yeah, it says it's still uploading. So let me just like reload the Dropbox page. I don't know why it's not going. Okay.
Hey, James.
Yeah.
Did you see that the file wasn't there?
Yeah, I just got it to upload. I don't know. It like got hung up on. It said like 2 seconds left for like the whole time.
Oh, it is there now. Okay,
It just
cool.
yeah, just got in there. I don't know why.
No biggie.
Mm-hmm. The original one is still trying to upload. So maybe there'll be a duplicate in like 10 minutes or something. Thank you, Walter. Max, you're asking about the component that I used to define the polyline windings. I've got a lot of components that I've made myself that I would like to share as a plugin, like on Food for Rhino one day. Got like 30 or so right now, so it's looking pretty good. I got a whole bunch of stuff. But I like made all of these like as I was learning C#, so like I kind of need to go back to the earlier ones and like fix them because they're probably really horrible code. But I do plan one day to like release a plugin pretty much focused on like computational geometry algorithms and some mesh and other utilities, curve utilities, and a lot of bounding geometry options. I like that stuff. I basically just did things that I thought were interesting for coding and put them into plugins. So hopefully I can release this someday. Just need to like rewrite some of the code, I think, and come up with a name for animals. So if you have a good idea, let me know. The once C# component you had to edit on the fly is going to remain updated in the download, right? I didn't replace that with another C# component. I just replaced that one that wasn't working with some regular Grasshopper code. So that'll be in the file. So you don't have to worry about that. And you can have the C# component too. I don't know why it didn't work, but whatever. We fixed it. All right, are we back at 2 minutes past? Okay, let's continue. Now, what we're going to be moving on to is basically the a lot of labeling. Like we need to label all these edges, like how we see here, where we've got N10D, N006D, and N6D and N10D. So see, these are matching tabs. The one that's in the box is the self, is the tab label of like this tab is N10D, and the one that it matches is the one that's outside the box. So then you just say, okay, I need to search for this, and that's this one right here. The labeling system is like the subassembly ID, the strip ID in the subassembly, and then the tab ID. So that's basically the way that we're going to do that. Let's see if I have another image of one. Yes. I'll zoom in so you can see here. See, this is C32A, and it doesn't have a matching tab. It only has naked edges. It's a naked edge tab. So this one doesn't have a matching tab that it goes to. This one is C32B, and it matches with C34F. We've got C32D, C32F, C32E, and C32C. So they're not like actually like in order always clockwise wise, but they the data works. So basically it's like this is from subassembly C, that first letter. This is strip 32, so all of these are going to have 32 as the second number on each tab here. And then the last one is which tab it is. So this is B, A, C, et cetera, et cetera. So it's like a subassembly to strip to tab hierarchy as the labeling system. And we're going to work on that. But first, there's one last little cut line thing we need to do. We're going to create, oh, we got to get those triangle holes. That's the one thing. Yeah. OK, let's get those. So we're going to copy a transform component. And triangle holes, we're going to get right from the unrolled component right here, from the unrolled curves back there. Let's see if that worked. Yes, it did. Look at that. It's so easy once you use the transform component. Once again, this newest transform component comes all the way back to here from the unroll poly surface, and we just get those unrolled curves that we moved along with our strips. So from this move component from the unrolled curves, we're gonna get all those. Those can go the cut outlines and holes. And nice, now that's part of it. So all these triangle holes are where they should be. And when you put this whole thing together, you'll get that nice gradient of holes from small to large in proximity to the attractor point that we did earlier. I will label this from quick save. All right, now we're going to make some relief holes. Basically, at each of these corners here, you may want to cut a little hole like I have shown here. So you see this like circular at each of the vertices. You may want that. I don't know. I think it kind of helps to stop for like ripping and tearing if you're using paper. I think it kind of helps. But we're going to put it on a toggle so you can turn it off and on if you want anyways. But like all these things, we got to start with one of these transform components. And what we're grabbing is pretty far back. It's right at the beginning of the tab thing. It's, I think it's these curves right here. So right at the beginning of the tab block, which is this one, you've got this curve component, which we use to merge and create the union region union. We're going to use that as the input for this. Make sure. Yes. It's just the original outlines, basically. The original outlines. Group this one, I'll say. From original outlines. And what we're going to do with this is we're just going to like explode it, get those vertices, and use that to place some holes, some circles. So explode, we're going to pull index, because remember there's like an extra vertice so that it can come back around. Like we got 1, 2, 3, 4, 5 vertices. We don't need that last one. So -1 on the panel as the indice input. That'll just always grab the last thing in the list. Yep, that looks good. We got a circle component. Put them here. Radius, maybe from 0 to, you know, probably the biggest you ever want these is like 0.25. But I'm going to put it at like 1/32 or something. That looks good. That's probably about as big as you want them. I'm complete this. So it takes the name radius. Unpreview some stuff. And now you see you've got these holes, but I don't always want them. Do a quick little stream filter thing where only if it's true do we add these. Like, watch this. Take that stream filter into the holes output and unpreview all this stuff, and you don't see them. But if I turn it to true, they show up. So now you could say corner holes, question mark, or relief holes, and you can turn them off and on. I'll leave them on because I think they do help, actually. They help because, like, you have a sharp corner like this, it's really likely to peel. You know, if it's paper, 2 layers of paper might peel off from each other. But if you have this, the angles between adjoining pieces are a little smaller. And then you don't have to do, you could just like do like a region difference or something. But if you're cutting it on a laser cutter, it doesn't matter. Like, you can just use the laser to cut this for you. You could do a region difference with these circles instead, but that takes more computing. Okay, I will call this optional relief holes. Yeah, that looks good. Okay, I think that's everything. If you're cutting sheet metal, yeah, I think people do this when they cut sheet metal, especially if you like have like tight bending radiuses. Definitely, I think people do cut relief holes. Although if I was doing it with cutting sheet metal, I'd probably take the time to do the region difference so that we don't, like, I don't know, you're cutting sheet metal, it's probably a lot slower, like a plasma cutter or something. So, you know, reduce the time, travel, don't have any useless cuts, you know what I mean? Save again. And now all the cut lines and fold lines are done. So it's time to create the labeling system, basically. Like in this photo, we're going to have to put them on each of the tabs. And the easiest thing to do first is to get the ones that have a naked edge, right? All we have to do is get that information for the points we unrolled, which is easy. All right, let me figure this out. Naked edge labels. Yes, I see it. Okay. Once again, start with a transform component. Going to be down here. Maybe I'll move this text, these text components further down. I'll move this down. Yeah, we've got all of our fold lines, or cut lines. Now we're moving on to the like text curves. The first thing to do is we're going to get those naked edge labels. Got to find out which thing I'm grabbing. Hang on. I think it's just those points. Yep. So all the way back from the unroll polysurface component, we've got the curves, the points. We're going to go for the points. So right here, these are the points. We're going to unroll those now and move them into place. Let's check. Yep. So this is a naked edge. That's a naked edge. That is too. That is too. So everywhere there's a point, that's a naked edge. We've got that information easily with that transform from the unrolled points that we unrolled with the polysurfaces. What we do there is we're going to put this into a, we're going to simplify it first off, because that data tree looked bad. We're going to clean tree, because sometimes you get, depends how, it depends. Sometimes you might get something that is like an empty branch or something, depending on how you bring those points in. Looks good. Yeah, see, we had 54 locally defined values. So we had a few empty branches. And now we have 30 locally defined values. So we got rid of those empty branches, which we didn't need. I'm going to flatten. So now I'm going to get a curve component. And that curve component is going to connect to we're going to get from this one right here. It's the original lines, right? It's just from this first transform component. We're going to get those curves. I'm going to display this as faint. And we're going to go into the C# one. And we're going to grab the one that says return naked edges by point proximity. Okay. Back to strip making. Go to zoom way out. Paste it. Grab it. Bring it over. Come on. Enable it. Basically, it'll just return the curves that the points are touching. So points, edges. And the edges should be flattened. And what it does is it gives us these edges right here. You see that? So just the ones that have the points on them, those are going to turn red. Oh, here, I can unpreview that. So just these ones, these are all naked edges right here. All these ones don't have a matching tab in this subassembly. So we just need to label those. And what we're going to label it with, first, we are going to get an extend curve component. Take this curve, reparameterize. The type is a line extension by default. This is where we are going to have to reach back a little bit. I'm going to get a panel and say it's x times 2 times -1. This will double and flip the sign of the stuff we're doing. We're going to put this expression into both of these, x times 2 times -1 and x times 2 times -1. Oops, didn't do it. Great. -1. Oh, I hit cancel again. Got it that time. And what we're going to take the start comes from, just got to make sure I'm looking at this right in my notes here. Yeah, I almost just got fooled. They both come from the tab end width offset. So if you remember that, that's all the way up here. Tab end width offset right there. And the end also. Oops, went too far. There it is. We'll faint these wire displays because they're crossing everything. Basically, that's just going to inset a little so that our text isn't like so close to the edges. We're going to use this to put our text places. And we're gonna, I gotta move down. We're gonna get a perp frame so that we can get like some planes on these edges. Reparameterize 0.5 is the parameter. So you get a plane in the middle of each of these edges, these curves. And we're gonna do the rotate plane by axis, which is from Fox, which you have if you're this far in, you have it, because you had to use the Walker component. You could use this other thing, but whatever. You could just like figure it out yourself, but I mean, this component does it for you. Rotate plane by axis, it's easy. We're going to use the y-axis, which is what you're going to put input here, y-axis, and the angle in degrees is 90 already, so we don't need to change that. Yep, that looks good. We're gonna deconstruct D-plane, right? This plane right here. And we're gonna get the y-axis as a unit vector, which it probably is already, but whichever. Amplitude on that vector. And we're gonna put another expression in. This is so we can get it like in the middle, basically. X times negative 0.5, or it'll be X times -1. So we'll see which it is. Just gonna put that there, and I'll put this as X times -0.5. And the amplitude goes to the tab end width offset as well. So back up here, back over here. A lot of things go into the tab end width offset, but it drives a lot of other stuff. So makes sense. Now I can move this plane by this vector. Okay, so that moved it the wrong way. So it doesn't need to be negative. That's where I want it. I want the origin of the plane to be like in the middle of the tab. See that? So instead of, we'll say this is X times 0.5. That's what it is. Good. X times 0.5. Yes. And now we're going to use text. And the text that we're going to use is also from Fox. They just have a pretty good text component. We're going to take that plane as a location, right? That's what that is. That's a plane. Yep. The text that we're going to do to label, you can say whatever, but this is what I used to label as a naked edge. I said just like N with 2 hyphens. That's a little too big. A little too big. I'm going to change it to 0.075. Nice. And the horizontal alignment and the vertical alignment are both 0. That's in the middle and center, which is what I want. Good. So we've got these naked edge labels there. Let me hide this frame. We are going to now grab a endpoint. Whoops, there it is. From these extended curves, right, which are these guys right here. Get those endpoints. We're gonna group these text curves just as their own things, so but we're also gonna simplify for sure. Got 30 naked edges labeled. We're gonna do move to point, which is another pufferfish component that just like replaces using like vector point and move with that. It's like so annoying having to do that. This is a nice component that just does it for you. We will flatten all these groups. Point A, we got to grab a point from here. This point is going to come from the origin of this one. Maybe I'll just make this look nice. Yeah, what are relays? I don't know. I just have a habit of like forgetting about them. It's okay. The point that we are taking is, this is going to be point A. And point B is the start. Yep. Look at that. I got that there. And we just don't want it in the middle of the thing because that's where this tab label is going to go. We want it to be like on either side. So that's just all we're doing right now. Great. That's what we want our naked edges labeled to look like. Let's check. It showed up everywhere it's supposed to show up. Yep, yep. Yep, yep. Good. Okay, so that's what we want things to look like, basically. Yeah, that's good. And now we're just gonna merge and ungroup. So it's just regular curves. Oops. Come on, let's see it. Yep, a lot of curves. That's good. Now we can hide all that. So there we go, our first text. Maybe that's a little too light green. I will darken it a bit. That looks good. Maybe I'll even up the thickness on the text just so you can see it better. Kind of hard. Yes, all the naked edges are going to be like this. And just the room in the middle will be so that we can put the tab label on itself and not be in the way. So all your naked edges are now labeled with like an N, so you know, okay, these don't connect to anything else. I'm going to move all this just back a little bit. And I'm going to say this is a group creating the naked edge labels. All right, guys, we are moving into home stretch, sort of. We just got to do the labeling and then the petals. We're pretty much done. Right. All right, time to generate some strip IDs, the tab self labels. They're going to be in the format of subassembly ID, strip number, and then tab ID, just like I said here. So like N010D, yeah, that's the subassembly, strip, tab. So that's the format. We will label each tab now. Okay. Tab self labels, a little complicated, but not too bad. It's going to start off with, we do need to reorder strip edges to match the original order. Sometimes they get a little jumbled up. It's kind of strange, but it's important that the things aren't mixed up because then you'll have like mislabeled edges. So back in the C# component, reorder strip edges to match original order. Copy that. Bring it in. It's going to be on the left, way over there. Got that now. You can enable it. We got to get some breadth edges. And I just know we're going to need to simplify it. What that's going to be, that's the guide edges. And this is going to go all the way from, I'm waiting for my image to load, all the way from way back here. Where? This one right here. This breps as list. That's what we're getting. All those naked edges. That is, I'll come back. You see, that's the 3D breps. These ones are in 3D still. This is like these right here. The reason that we have this is that we know which things are touching what, basically in 3D. They're 3D proximity to each other, which you don't have anymore once we are flattened. So we grab it from here at the end of the reversing strips group, ensuring that there's no reverse strips group. We grab those breps. I'm going to turn this to a faint wire. Got to move it. Got to get back into my notes here. And that follower curves, let's check this. That's simplified and nice. So I'll simplify this so that it matches whatever it is. That's going to come from the original transform, which is just those original outlines where you move up, 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 up. From right here, this one right here. We get that. Change this to a faint wire. This just is going to reorder strip edges to match the original order. Is for each guide curve, look at all the follow curves, and then add the follower to a list if it matches the current guide curve. This was like really annoying. Like things just get like reorganized for some reason when you like do some certain operations in Grasshopper. So then you have to like go back, reference the whole so you can get these like part-to-part relationships again. We're gonna now take these and generate the labels. So get a curve component just so not everything is spilling out of this one component. We got a lot of stuff for this. Not too bad though. First, we got to get perp frame. We got to have a location for the text that we're going to have, just like we did last time, basically. Reprioritize 0.5 because that's the middle of the curve. Now you see we have one at each edge, at each tab. Basically, there's a frame. We're going to rotate plane by axis. Plane. Let me just get this. Hey. Same thing. And the text. And I grabbed it with the font size because I know that's what I want it to be. Same font size. But we don't need it to say N for naked edges because that's not true. So first I will just get rid of that. And now we're going to have to generate the text. And the way we're going to do that is going to get a text component and all the way back. Oops, shoot. I unclicked. All the way back here. Nope, not that one. All the way back here, the data dam, the original data dam. Remember, we sent this identifier, the subassembly identifier, along with it, that text, just the M. We're going to get that. Bring that down. Oh, we're still even further down. Pop that in there. Make that a faint wire display. Don't need that to be so crazy. Gonna get a list length component on each of these tabs, so we know how many tabs there are, basically. We're gonna do a repeat data because we know that the first thing that each tab is gonna get and have in common is the subassembly identifier. Every tab is gonna have that. So we can make its list length as long as the thing, as long as we're gonna put this on every tab, essentially. That's all I'm trying to say. We're gonna concatenate component. We're gonna have a few of these as we build out the tab IDs. So right now, we'll get a panel so that we can look at what we're doing. Each one just says M. We're going to put a hyphen as the joining fragment, basically. So we're concatenating M with a hyphen. We're building that label out, basically. We're going to get an item index and a expression component, which I hate using these. I find it very confusing. But let's jump in there and type this correctly the first time. X. Only one thing, and it's going to be like this: 0, 1, 2, 3. Okay, let's check. I think that'll work. Oh my God, I hate this. This component comes in, and it's like incorrectly labeled. It's so weird. Variable X. Yeah, there you go. both of these are going to come from the split rep C# component, except remember we broke that. That didn't work. So where it's going to come from is this thing at the end of the reversed strips. One, list, and item, index. Whoa. Come on down. Now we'll figure out what we did wrong. Why is this thing complaining? Premature end of expression. Oh, whoops, I forgot the quote. See, that's why I hate this thing. This is exactly what your thing should look like. I messed it up. All right. Got another concatenate component now. This is basically like getting the index of each rep, which will be the strip. So this will be the next thing is the strip number, right? So if I take the results of this and I graphed this, I put that in there. Look at that. Look at that. I think I need to flatten something. Let me just check. No. Well, we'll continue. Continue on. Yeah, that's what I need to do. So flatten both these inputs so that you have each strip has its own number, right? Yeah, that's good. Now we get another concatenate. We're going to take it from there. I don't need it attached to this, and I don't need it grafted because all we're adding is another hyphen. So now it looks like this. We're building it out slowly. And one last concatenate component. We'll disconnect this, excuse me. One last concatenate component. And what we're going to add here is a length. A series where the start is 0, step is 1, so that's not changed. Count. And this is basically counting how many tabs there are in each strip, which is the last thing. And we're going to put a text component. And in this one, we're going to type the alphabet again, but lowercase. So that's the alphabet in lowercase. Oh yeah, you can add inputs for concatenate. That's right, I forgot. Yeah, you can zoom in and just do it with one. Oh well. We're gonna get a list item. The list is these, the index is the series. Put it in there. Now I've got A, B, C, D, E, F, G, H, et cetera, et cetera. Why did I reverse this in my last one? I don't know. I guess we'll see if I need to reverse it. In my notes, this input is reversed. So I will reverse it. I don't know. We'll see if there must be a reason for it, or maybe there's not. Right, so we've got all the tabs and strips labels generated. We're going to put this into the text. Let's see what we get. A, B, C, D. basically what we're looking for right now is to make sure that there's no like skipped letters. And it's like, this one only has 4 tabs, so we only want it to go A, B, C, D, and those are there. It's okay if they're not like in order. We just want to make sure there's no like wrong ones. So A, B, C, D, E, F, G, H. Yeah, I think we're good. I think we're good. We're not like skipping any letters, and we're not adding any extra ones or anything like that. So those curves there, we're gonna deplane. Just like last time, we need to like move it just into the center of this. Yeah, deplane. Get the unit vector, the y-axis, amplitude here. What did we do last time with the amplitude? Where's that? I'm just going to copy that. I'm going to copy it because it's already plugged into the correct thing. It's the same tab end length or whatever it was. Just copy that in there. We don't need to go searching for whatever this is plugged into. And we're going to do a group. Oops, wrong thing. Group of the text objects. Shift paths. Look at the thing, it's kind of messed up. The data tree isn't how I like it, and now it is. And we'll do a, we'll do a move. Move the text by the vector. That's good, except it's all upside down. Now why it's upside down? Good question. How does this rotate it? All right, whatever. I'll just do a rotate geometry by this plane. The angle is pi. It's pi. If you want to do radians, it's the other way. If not, it's 80 degrees, 180 degrees if you want to do degrees, but I know that it's just pi. Now our vector does need to be negative because we rotated at the end, so let's do that. Yep. Now it's looking good. We've got our text aligned and in there. This naked edge is done, basically, right? There's not going to be a matching thing for it. Oh, it's not quite done. Yeah, we're going to circle this tab name so that we don't get mixed up when we're looking for, this is the tab name and this is the one it matches with. We're gonna do a convex hull around that. So explode. First, we gotta ungroup the text. Simplify. Another shift paths because this thing got changed. And this can go into the text right here. So we can hide that. Look at that, looks nice, looks great. Only thing we need now is the little line that goes like around it. Yep, that looks good. So this way we can circle like the whole text. And that way, like this tab is the one that's going to be circled. And then the one that it matches with is the one that's uncircled. We are going to offset this curve just a bit because it's kind of touching. That's too much. 0.03 or something like that, like a small distance, doesn't need to be big. Yeah, that looks good, right? Okay. So now you'll know the one that's circled is the label of this tab. This is like this tab. and then the one that's uncircled is the one that it matches with. So we'll put that in the etch too. All right, now this I'm going to label as creating tab self labels. So you know these are the ones that label the actual tab itself, not its matching tab. Things are looking good. Yep, just checking on everything. Everything looks right. Okay. Now we move into probably the part that I find is the most complex. When we were designing this, my partner at Immersion Design, Jason, he had to help me with this. It's the finding the matching tabs that these go to. He's like a data tree wizard, and I'm like sort of like not so much. So I was like, you have to help me with this. So even now I find this part to be a little complex, but probably some people won't. We're going to find the matching pairs of edges, right? So we know which tab goes to what other tab in the subassembly. So we do have a C# right here, find matching pairs of edges that we're going to use. So back in the C# doc, grab that one. And once again, we're going to zoom out because it's going to come way over here. Pick that up. Get it. Enable it. And basically this will take in a tree of edges, and branch for strip and count and branch is the naked edges of that strip. And for each edge, find the matching edge and log its data tree index to a string tree. And now you have the matching strip / edge index for each strip and edge. Probably confusing, but if you know how to read C# code, you'll see what this is doing. Otherwise, you don't have to really worry about it and just know that it's magic. So see how each of these data tree outputs is either 2 or 1. If it has 2, that means it has a matching edge. If it has 1, that means it's a naked edge. So everything that comes out of this will either be 2 or 1. We're going to go for a list item from here. We're going to get both the things, right? Now we got to do some text split operations, because what we've got out of here is some text as indexes, because we're going to try to retrieve some items from a tree. So we're going to need the path and index of those items. And what those items are the, the IDs of the tabs and their matching tabs. So we're going to need to decompose this text. So let's get a text split. Whoops, split. There you go. Can I hop in here? No, it's not like the concat component. Okay. The text we're going to split, start with this, and we're going to panel. First things first, we don't need that. That's an open bracket, right? Now the result of that, you'll see, is like this. Did I put an enter or something? Whatever. I don't know why it does like an empty. We're going to take that text and we're going to split it with a closing bracket. We don't need those. So now you see that's what it looks like. We're going to do it one more time and get rid of that semicolon in the middle. Don't need that. Now you'll see we split it into these lists where it's like the index and then the path. Kind of tidy this up a little bit. And what we're going to, oh, wait, I did this a little wrong. That's why it has all these things. List, item. We're going to need 3 of these. This is the list. And the index we need from this is the first one. Right, this is how we're going to not have the empties. This output goes into the text. Okay, I'll give it a little bit more room so people can see what's going on. It can be a little confusing. Okay. So this comes out back into here. This will come into here. We only need the 0 first item. This will come into here. And for this, we only need the first item. Look at that. These are all our indexes of the tabs, or the paths. Sorry, the indexes are the second thing we're going to do. Right. So let's do this. Simplify. Simplify. Right. Good. Now we're going to do the same thing, basically. Yes, the exact same thing. So all you have to do is copy, paste, and do that for this output of the matching edge pairs, right? And this is going to give us the indexes. So this is the paths, and this is the indexes. Good. I told you it gets a little complicated. We're going to get another perp frame, replacing some text. Perp frame is going to come from there. Perp frame comes from the this C# reorder strip edges output. Reparameterize and set that parameter 0.5. Get that midpoint again. I'm sure you could, we're like doing things that we've already done before, but it's like, if you don't want like a mess of spaghetti, it's kind of just nicer to redo a few components rather than like, I could grab this from like, somewhere in here, I'm sure, but it's like just like a cleaner script in the end. We're going to need this rotate by plane again. Copy one of those. The frame is this. The plane is that. Yep, that's looking good. Here's the thing. I don't know if you guys have this component. For me, it's in my regular sets, but I think it's from like Tree Sloth or something. When I look at it, it looks good, but when I Googled it, I didn't see it anywhere. So I don't know if this is like a vanilla component or not. I have no idea. So I like rewrote its ability. I rewrote it in C#. So you can just get it from here. I don't think it is a vanilla component. So I think this is probably good that I rewrote this. We're going to zoom out. If anyone knows what plugin that's from, I think it's from Tree Sloth.
Yeah, it is.
Yeah, it's a pretty good plugin. I use all other stuff a lot, but I just rewrote this one in C#. So I had a hint that it wasn't going to be there, and I didn't want everyone to be like, oh, don't know what we're doing now. We're going to need 4 of these. Yeah, we're going to need 4 of these. 1, 2, 3, 4. Oops, that's 5. Well, goodbye. All right, and what we're going to do with these, we need 1 up there, 1 down here. All right, yeah. Just like spread them out a little bit. Yep, nice, looking nice. Delete that. We're going to take this list item, plug that into the, oh wait, first let's get the trees. The result of these is the first 2 trees, right? This text for the tab labels is the first 2 trees. And the path for the first one is the I output of this list item. And the index is this one. Oh, I'm so glad that turned green. I mean, gray again. I was like, uh-oh, when it turned red. And there's some correct outputs. Ah, it works. The second one we're going to get from the second batch of this list item, path, and index. Yep, looks good. And then these 2, the tree is going to be these planes. So plane, plane. And the first one, path index from the first one, just like we did with the text. Yep. And the second one, just like we did with the text. So what we've got now is these tab names and these planes. And if everything is as it should be, we should be have these things like matching the correct tabs to the correct tabs. And the way that we did it basically is all due to this find matching pairs of edges, which comes from that 3D rep. And that's why we need to reference the whole to find out which parts go with which parts, basically. It's like in 3D, it's easy to tell which edges touch, but once we flatten and nest them, they're no longer touching, so you don't have that data. So this C# component is the key to get these matching edge labels, which we're going to see in just a moment. Let's get another one of these text, and I'll keep the size. Right, so I'm just going to group these. And oops, I said bake. Shoosh. Oh yeah, it's just text, nothing bakes. Group them. This is text, and these are planes, just so I'm not confused when I'm trying to pick which thing goes to what thing. We're going to go from the second C# component, and the location is going to come from the first one of these. Look at that, M12D, M2E. So those are like combining, basically. That's nice. That'll be what we want to see. Yeah. We're going to get another one of these down here. And location is going to be these planes, and the text is going to be this text. That looks good. Yep, nice. Excellent. That's what we want to see. We're going to do a D-plane, 2 of them. One from this planes and one from this planes. I'll move this down so these can be sort of straight out. Maybe just move all this up. No, that doesn't look good. Okay. From here, we're going to take, because we got to move the text, right? Because it's not in the right spot. Hide this so you can see the planes. No planes, I mean. We're going to move the text, obviously. That's what we're going to do. So I will copy these because I know that's what we're going to need to be moving. And the vectors that we're going to need to move them along, we're going to need to change the amplitude. Just like how we did for all the other text, you need to move it half the distance of this tab. We're going to get the y-axis for the vector. We're going to get the y-axis for the vector. Yep. We're going to amplitude. I think these are going to be from the both from the tab width thing, but let me just, I just want to see it. 0.125. Oh shoot. Negative. Give myself some room here. I'm probably going to replace these with the something from earlier. Like I'm going to get it from here, I think. But for now, let's just see if this is right. Move. And move. Right, so that moved it backwards, so it doesn't need to be negative. That looks good. It's just on top of the other text, so we'll change that in just a sec. Yep, we're going to get another amplitude, 2 more of each, 2 more moves, because now we need to move these like to the side so they're not overlapping like this. These moves are going to be from the geometry that we just moved just now with a different vector. The vector is going to come all from these x-axis of the planes that we had. This one too, x-axis. Clean things up a little if I can. Doesn't look too bad. That's a little too far, like they moved quite far. I'm going to one, just to change that amplitude. We'll slide that over. That looks good. I am gotta rotate these planes because it's upside down text, so I need to rotate those. Angle I. The geometry is the plane is the plane. We'll change it for all these things. There you go. So something I did is different than what I had in my notes. Like things are just like either negative or not, and like the planes are rotated, but it's not so hard to fix. It's not so bad. We are going to bring back this negative number now because that'll put these right where they need to be. All right, check that out. All of those, let's make sure that these match, right? So we're going to look at one of them, like this one's M28D, and it matches with M26C. So if we find M26C, it should say M28D. So let's look for M26C. Just looking for 26. M26C matches with M28D. Okay. 26. Nope. (26) 26C, M28D. Look at that, guys. Right there. So now we know that the matching works. If you want, we can look for another one, but I am confident that they are correct. So we just checked M26C and M28D. Those match. Let's make sure I got that right. M28D, M26C. Oh, yeah, very nice. So that is the matching text. And now we can put that right into the text thing there. Pop that up. It's a good feeling when things work out. I remember when we were developing this script originally, this was like very nice. You can hide all this stuff and group it and say generating matching tab labels. So this was generating the tab self labels. This is generating the matching tab labels. So the way the system works is you look at the one that it is, and you look at the one that it goes with, and you find that one, and it will have the opposite. All right, that is done. Now I'm going to save, and there's only one thing left. We're not quite done. We still just have to unroll and add tabs and nest the petals. But that's pretty easy after everything we've done. There's no labeling needed either, because the 3 typologies, the 3 sizes of the holes, makes it easy to know what petal can fit where. So we're going to go do that. Just got to go scroll. I have a huge like high-res image of this Grasshopper script that I'm like referring to write it right now. All right, excellent. We're going to do this maybe over here in this part of the script. We're going to get the unroll poly surface from Pufferfish again. Get the surfaces, and what these are going to be all the petal geometry. That's why we baked them as surfaces, right? So I'm just going to select objects, set multiple surfaces. I can lock and hide these again. Poly surfaces into there. A little slow because it's quite a lot of them. That's okay. If we go into the top view, you'll see them there. And see how there's only 3 sizes? Just know that these are like stacked deep. There's like a bunch of each kind. Okay. We can simplify. Well, maybe I'll just get another surface thing. Just flatten. I'm gonna flatten these. The way that we're going to do this is like I'm just going to count how many of each kind there are, and then nest them that way. Basically, I'm going to get the area of these, and there's only going to be so many areas, right? If I do create set, that'll get me all the areas. Nice, there's 3. Sometimes there's like 4 if there's like a little bit of like math error, but they should be like very close in number. So you see there's only 3 areas out of all of these different ones. There's 2,059 different petals, but there's only 3 areas because there's only 3 sizes of petals. So perfect. And now we can do a list item, get all 3 of those areas, and we can do a member index search on the set of the areas with each member. So we get the indexes of all those ones. So do that twice more. And there we go. Now we have the indices of all of the services by their size, like by the typologies that they have. And we can get them exactly from the list item, which we use here. List, index. Look at that. So now I've got 601 of these sized petals. And I've got no values. What? Did I do this wrong? Yes. Oops. There we go. And I've got okay. I've got 1,042 of these sized petals. And I've got I keep putting in the wrong thing. $316 of these, the large size petals. I know it looks like it's selecting all of them, but it's just the biggest one you can see here. Okay, so now I've separated them into like by their typology. Can hide that. And what I'm going to do is, it's like a lot to nest all at once. You know, like 1,042 would kill my computer. 601. We can maybe do 316 of them. What we're going to do is construct prep. We got to add tabs to these. It's not going to be so bad. Debrep. We're going to do the tabs in like a sort of easier way. Dispatch. Because the edges are always going to be in a certain order, right? There's planar curve and line-like curve. Here, I'll hide these. Right, we're doing the biggest ones only. So there's always going to be this curve, the arc, and then 2 line-like curves. And it's always going to be in that order, as you can see, always that order. So we can just do a dispatch pattern that's like true, false, false. And you'll see now, this is the arc only, and this is the 2 lines only. So we can rely on that to be like that. I mean, you could always just also just check if it is a line or another curve, but this works just as well. Once we have that, once we have that, we can clean tree on list B, because some of them might be empty. And we're going to offset curve. The distance 0 to like 0.25, right? Maybe I want a few more decimals. We'll set this to be like 0.125. This is going to be the like tab length for the petals, right? It doesn't need to be as big as the tabs for the actual strips, because these are like sort of like smaller. These are like just press fit. I'll call this petal tab length. You'll see now I can, offset that. That's good. 0.125. We're going to now do a subcurve, which is like, we could have done it this way before, but whatever. I'm going to do 0.1 to 0.9 as the domain for this subcurve. You'll see that it's shorter because it's a subcurve, right? Look at that. That looks good. Maybe I can hide these things. Where's that plane coming from? I hate that. Oh, there it is. There you go. I just like hate looking at the planes from like offset components. It's so annoying. Right. Back to this. We're making the tabs. We're gonna graph this output, and maybe I'll simplify it as well. We're gonna get the endpoints from these curves, right? And we're gonna get the endpoints of this curve as well. Check that out. Check that out. Check that out. Oops, I didn't parameterize this. I should. Although I don't know. Maybe you don't need to. Now we're going to draw lines from this start point to this start point. Is that right? Yep. So you got one there. We can draw a line from this end point to this endpoint. Look at that. That looks good. And great. Now we've got our tab like lines, basically. You see that? That's good. And now we can do a merge where the first one is going to be from list A. We're going to simplify. First one from list A. Second one from this line. Third one is going to be from this subcurve. Fourth one from this line. And now we've got, look at that. That's like that outline that we need, right? Because these original ones are going to become fold lines. So that looks great. Now we can do a curves. I'm going to flatten. Nope. I'm going to flatten. Going to do a clean tree. Yep. True. Is that right? Doesn't seem right. I think I did something a little wrong. I think I didn't like simplify something. 1, Can I simplify this? What will that look like? I think I probably got to do a little path shifting. Let's check it out. Yep, that's all I needed. All right, we got to just fix the data trees so that everything matches, so that we don't get like a weird thing at the end. Give myself some room. Don't need to simplify that anymore. This one is coming in strangely, so let's shift paths. And I'm going to simplify the input from here. Let's check it out. That looks great. Put that on. And same for this last one. Oops. Good. Now let's see. Why? What did I do wrong? How come some of these are invalid? I'm gonna bake them and see what I get. Yeah. Don't bake invalid objects. 54 curves. That's not. God, where'd that go? I see. So okay, so not looking so good. Cell open curve. Have some open curves. I don't know why that didn't say. What is this? Valid curve. This is a closed polyline with 234 points. All right, something's not right. We got to fix this. Not correct. What do I have here? Like, what's the problem? Moving backwards, we've got, these are the surfaces. We get those edges, dispatch them. What happens if I simplify this? Okay. Okay. We're going to solve this. We've got some issues here. Okay, maybe that's all I need to do, hopefully. Fingers crossed. I probably don't need these now. Wow, what's going on here, folks? Let's check this out. 315 with one each, 315 with two each. Things are looking good there. We do need to offset both of those. Everything needs to be shifted. I don't understand it. Put that in there. Okay, that looks better. Come on. Now we're looking good. Okay. Just gotta make sure your data trees are like all matching, because sometimes you'll get some weird issues like that, and just a couple of shift paths will save you. Right. So looking at this, we've got our nice exterior curve there. Now we just got to how many do we have? 316. It's kind of a lot. Of things to nest at once. Maybe I'll just like split and take just a few, but for now, just got to go up here and grab the nesting group. I'll bring that down. Bring that over, disconnect from the geo, because now we're going to nest these. Oops. Now we're going to nest these curves, the petals. And I don't know, 316 might like crash my computer, so I'm going to split the list at like, we'll start with like 100. I just want to gauge how well my computer is going to be able to nest these things. I'm going to save for sure. And let's say we're cutting them out of the same material, so the same paper sheet size. It's just some colored Bristol or something if we're doing paper. So I'll nest that. Okay, that was really fast. So actually, I feel pretty confident. Let's also move these up in unit Y, like 25. Oh wait, 19. Because this is a 24 by 18 sheet, so we move it up 19 inches so that we can have the petals next to the other geometry and they're not like overlapping like they are now. Let's just check. Looks good. Oops, forgot to. All right, look at that, guys. I'm going to go ahead and put in all of the petals. Take a little longer, but it's only 3 times as much, and this only took like 1 second, so don't crash, please. Let's see. Any questions? Yeah, no. Wow, this is taking longer than I hoped. Good thing I just saved. If anyone has any questions, oh, never mind. And look at that, guys. We've got our petals. Now all we need to do is bring in those fold lines for those. And you could, of course, like up the tolerance and spacing so that you get it like much nicer, like change the iterations from 1 to 15 or something. And then you have like a lot better. You'll probably be able to fit these into 4 sheets. Let's get the fold lines. Transform from here. Oops, I plug in the geometry. That should be the transform. Graft, always from this. Simplify. I don't know why it's like such a crazy data tree. And the geometry we're grabbing is list B. Is it? Yes, it is. Okay, great. And we got to move that up too. Look at that, folks. So we've got our petals now. Maybe actually you'd rather use a different one for this so that you can put these on different layers. Like this will be a cut layer and this will be a etch layer for the fold line. And I'll save this. And I'll hide everything I don't need. Preview off. Save it now. I'm going to also get rid of this. Great. So now you got sheet, cut line, fold line. We've got our petals. And you just have to repeat this step for the 3 petals. But like this one has 1,142. So like I'm not going to do that live. You know, this would take a while. I mean, the computer will do it, but it might take some minutes, you know, so I don't want to do that. There's no reason. You see how it's done. You can do it. And we've got our parts. And so this is one subassembly plus all the petals of one typology. So you'd see how you could do it for the rest of the geometry, the rest of the stuff. But I think that's pretty much everything right now. Yeah, we've got the relief holes, got the naked edge labels, et cetera, et cetera. Things are good. Oops, don't need new, just save. Yeah, so that is the entire workflow of how we did core light. You would just need to now go through each subassembly and like optimize, and it should do everything else automatically completely. The only thing you need to run manually is the Silvereye or Galapagos thing for optimizing the strips. But there's probably like a way that you can make that happen automatically. I've never needed to, but that's it. That's everything. I'm going to name this flattening, packing, petals. Right. That's everything. I guess we can do questions now. Any like open questions or something, like we can like go live.
Yeah. Hey, that was really cool to see in depth. I know we had a little taste of it at the last CD Next.
Yeah, but that was cool. Like, yeah, that was nothing. I mean, this is like I skipped over everything basically in CD Next.
Yeah. But it's also really nice because you don't often see in videos and webinars like from design concept to kind of like fabrication.
Yeah.
I mean, you started with like just some people standing in a room, and then all the way to the kind of layout of the construction pieces, which is really
like nice. Literally ready to hop on the laser cutter.
Yeah, you're gonna have a bunch of core lights popping up around the world.
Hope so. I mean, it would be cool to see if anyone does build something, even if they like scale it way down. That would be really cool. You could make a desktop one.
Desktop core light.
Exactly. We did like some tests, like real small scale.
They're for your cat.
Yeah, yeah. You can make a cool cat furniture.
Okay, so firstly, if anyone wants to ask a question and be awesome live,
yes.
Just click the raise hand button, and we'll bring you here. If you want to ask a question or have some conversation, please just raise hand. Don't be shy if you really have a question. Sometimes no one wants to ask questions live.
Come on, don't be afraid. I just talked live in front of everybody. You can't even see each other, so it's like I might as well have been alone in a room talking to myself.
Yeah. So you have a question from Walter in the Q&A. There's one there.
Yeah, let me see. Shedding and molting, they see vastly different in purpose and technique. I think he was saying this as for a name for like a Grasshopper plugin. All the animal names are taken. It's true.
I'm surprised I got Pufferfish after so many years. I don't know how no one used the name.
Yeah, that's a good one. How do you determine the thickness and strength of the material? If you needed to, like, let's say you're using something thicker than paper, right? We didn't have to account for any thicknesses for anything. I think all you'd really need to do, well, I mean, despite, if it was something with like some bending, like in sheet metal, I think they call it like the K factor, right? Where you're like bending and like material like bunches up and can only bend so far. But if you're using like just like thicker paper or something like that, all you really have to do is offset these original curves half the thickness inward, I think, before you do any of this stuff. Because then when you put them all together, the thickness of the material will fill up that gap. But if you're doing something like with like real sheet metal, there's probably some more considerations you need to take into account, like the I think it's called the K factor. I don't know why I think that, but it's like some sheet metal bending thing. When you like bend sheet metal, it can only bend so much or whatever. So how you determine the strength of material, I mean, you do some tests. We did some tests. Not everything can be computationally defined. You know, we had to do some scale mock-ups and prototyping for this with the laser cut Bristol paper until we found like, you know, appropriate triangle sizes and all sorts of material properties like the dashed fold lines versus the scored fold lines, et cetera, et cetera. So some things you do need to sort of just like actually do. I don't know how accurate like FEM stuff would be for like determining paper strength. Probably not quite accurate at all. How can we mark up the triangular holes based on their size? The nice thing about only having 3 sized holes is you don't need to at all. It's really visually easy to tell, and you can only fit 1 size petal into 1 size hole, and it just won't fit otherwise. So you don't need to. You could, if you wanted to, like for each of the sizes, just pop a little like, you know, 1, 2, or 3 next to it or something. But there's really no reason to. Since they're all just equilateral triangles and only have 3 sizes, you know, you can only fit the petals into their proper sized hole. So if you had a bunch of different sizes, you could do what I said, where you just pop a little number next to it, like labeling which typology of hole it is. That would work. Are there alternatives?
Yeah, they could just use they could just use what you taught them for the other labeling. It's like kind of the same idea about positioning. And it's just a lot simpler because I don't need to label it so complex. It's just like 1, 2, 3.
Right. Yeah, you wouldn't need to like find a matching thing. You just like go by the sizes or stuff. Are there alternatives to the flaps for the joinery component? Alternatives to the tab system? I mean, like you could probably figure out something else. Yeah, like the way that we did it with these tabs. Where is the picture I was just showing you guys? Yeah. So like we did it, this is like an inverted version where you see each tab like joins up and gets binder clipped together with its match. We did this, but everything was on the inside. The tabs go inward. And the reason we put all the labels and stuff on the tabs is so that when you put it all together, then you can't see any of that data, you know, all those like labels and stuff, which like makes it kind of look ugly. We put it on the tabs, which then get folded inwards, and then you can't see it anyways. An alternative, you could probably like, if it was stiffer material, you know, welds if it's metal, joinery if it's wood paneling, maybe even like zip ties if you're doing like some sort of plastic sheeting or something like that. Rivets,
Probably find a way to like slot it.
Slots, yeah. You could do all sorts of things. This was just chosen for ease of assembly, and like it was very cheap to do it this way as well. All we had to do was buy like 2,000 binder clips off McMastercar, which was only like what, like $5? No. Yeah. But they're so good. I love McMastercar.
Yeah, and it's like you would have less material if you did a slotted system, but a lot more difficult time putting it together.
Yeah,
because like you have your hand inside of like the hole, and then you have to have your other hand outside to kind of like slot them together. Whereas this, you just need one hand to just clip, you know.
Mike, where can I get a design morphine hat?
Right. I haven't seen anyone using these clips for an installation yet, so you might be the first one. You should make another full one with the clips on the outside. Could look really interesting.
Yeah. No, Mike, where do I get that hat you're wearing? You got to email me about that later. Yeah, so there's plenty of ways you could do it.
You know?
That's sick. Yeah, we chose the binder clips because it was like we had a lot of friends help us assemble it. Free labor, you know, we just bought them some pizza and beer, and this way is like real easy. You know, you just tell them, okay, like you see the tab name, look for the tab that says this, and then clip them together, and everyone gets that. So it was really easy. You don't have to worry about like is the slot aligned right? You know, it's just like if you push that binder clip up to the base of the tab, you know, that's done.
Yeah, I mean the other with if it was metal, you can do kind of what Fornace does, which is like the riveting for 10,000 years.
Yeah, you could use like 1 billion rivets. Thanks a lot, James. I learned a lot. I got a bit lost at the end, but hopefully you will share the finished files with us. Yeah, I definitely will. In fact, let me pop them in there right now while we talk so anyone can download them.
They're very, very nervous that you won't share this file with them.
I will. I'm going to right now. And I'm going to rename
No, I'm
it
just saying,
to,
like, they ask a lot. It's funny.
no worries. I changed the name to strip making final, and I'll change everything to final _final, working final.
We wouldn't leave you guys hanging like that.
It's really weird that you can rename a Grasshopper file while it's open, but you can't rename a Rhino file while it's open.
I also never understood that. Like, you shouldn't be able to do that, actually. I'm pretty sure that something is going on wrong there.
Yeah. The Rhino file hasn't changed, so it's still the same Rhino file. Did it upload? Yeah, form finding file, strip making file, final. How long did it take you to put your piece together after all the laser cutting was complete? Let's see. We did, this was our presentation that we gave when we like unveiled it. And we have all the stats of like how long everything took, and you'll be surprised. 50 hours of laser cutting for the original core light. That's like me in the laser cutter running 2 lasers at once, 50 hours of my time, like standing in the room. Then we had 2 days of building, which was 64 man hours the first day and 80 man hours the second day, which was 144 hours total. It's a lot of clipping and a lot of like, you have to like fold the things first, you know, to make sure the creases crease right. And then putting in the pedals is pretty intensive too. But it wasn't so bad. You know, it's really only 8 hours and 10 hours. You just have enough people to help. And yeah, so it took quite a long time to put together and to laser cut. I mean, that was like horrible. I was in the laser cutter until like 2 a.m. for like a week, just every night.
Breathing in those fumes.
I know. Yeah, it wasn't good. At least it was just paper. Can the same techniques be applied to architectural facade elements? Absolutely. See no reason why not. Just got to make some interesting base shape to like then mesh triangularly, and then you can make it into strips. You know, they can be much larger strips, like the triangles can be huge, and then at the architectural scale.
I mean, there's 2 levels. There's like the base geometry, and then how you change that for construction. So you would just have to, the base geometry would be the same, but maybe you wouldn't be making the same kind of tabs, you know?
Right, yeah.
If it was for a facade, you'd be using like a material that probably has a lot more thickness. And,
yeah, so you would have to account for thickness of things, and probably insulation is going to be a lot different. You're not going to use binder clips. But yeah, for sure, the same techniques can be applied in general. You just have to account for different things. So we have to follow all the steps for the other component, as here you have done the script for one component. Are you talking about for like each subassembly and each pedal? Yes. I'm not going to actually do the whole thing. It was a lot of like hours of, you know, to do each subassembly. I'd have to just repeat the same process over and over again. The only thing that you really have to like wait for that isn't automatic is the optimization step. I've read that you can use Galapagos through code. So like there is definitely a way to like loop through things and use it, but I've never done that before. But if I like had something with more than like 20 subassemblies, I think it'd probably be worth figuring out how to fully automate the process.
Then after you automate, you just plug it in.
Yeah.
Plug it into the same definition.
Yeah, I mean, I've read somewhere that someone has automated Galapagos. Hi, James. Is it possible to cluster the entire either steps or strips into 2 or 3 clusters for the variation materials, something similar to very many language? Cluster the strips into 2 or 3 clusters. Are you talking about so you only have like, I know when like people are panelizing like a facade of a building, they'll like group panels into like, you know, so you only have so many unique panels. Are you saying like unique strips?
Yeah, I think it, because like what very many does is like, for instance, like different like parts of the kind of strip graph are a different color.
Yeah.
So I guess in a way,
I've seen
like
that.
accentuates the strip.
Yeah, you
And
could do like a
like
secondary
they're
layer
all
of
white.
information. Yeah.
Yeah, like you
You
have
could
them
do
all
it.
whites,
Yeah.
right now.
You could do that by like distance to the floor or something like that if you want it to be like a gradient of color. Or yeah, I mean, by proximity to some attractor curve or something like that. If you're asking to cluster them like how they like do like panels on buildings, like so there's only so many unique clusters, you'd have to figure out a way to mesh it so that there's only so many unique triangles, and they're, so then the strips are made up of only like certain types of things. There's probably ways to do it, but it becomes a lot more complex. But that's probably not what you're asking, because that would be crazy. Any recommendations for a budget laser cutter that you have used? No, luckily enough, we were able to use the facilities at a local makerspace for this project, Artisan Asylum in Somerville. Shout out. Really great. Thanks, Lars. He is the director there. And we were able to use the machines like after hours and like just go crazy on them. They have two Mad Cats lasers or Black Cat laser. I can't remember, but I don't know how budget it is. They were huge. They were big machines. Have I tried
Yeah,
the Ivy plugin? Oh, sorry. Go ahead.
lasers. I mean, lasers are not really. I mean, there's some desktop ones, but they're not really. It's not like a 3D printer, like where you
Yeah.
can just get like a. Because lasers have a lot more issues.
And a lot
Mostly
more
fume.
dangerous. Way more
Yeah,
dangerous.
mostly fumes and heat.
Yeah.
So it's not common that you'll just find like a people having just like desktop budget
Yeah.
lasers. I
Budget
mean, they
laser.
exist, but it's just not really common.
Yeah.
And I would actually say the desktop ones aren't budget. They're like super expensive because they have like all kind of weird fancy ways to solve the exhaust fume problem. It's like those like smokeless ashtrays or something,
Right. It has to like carbon filter everything or something.
Yeah.
Have I tried Ivy plugin for strips? I have Ivy installed for some reason. I don't think I've ever used it. I must have at one point for something. I like download so many plugins just to see if I'll like it and try things out, see if there's anything really cool. I have not used this for strip making. I haven't. I know you can. I know that's like what it's for, I guess.
I
But
think Ivy
no, I
would be a
haven't.
good way to make strips like that you can identify as different like colors or materials.
Oh, really? You can get like some more
You can just
control
like
into.
make like fancier, nicer like, pattern. Like if the pattern of the strips matters, then
I see.
But in your case, it was more about just like being able to build it efficiently.
Yeah.
But if you really wanted like to play with the patterns, it just uses like graphs to generate different strip patterns.
Have you found a way to work between SolidWorks and Rhino/Grasshopper? I've tried using patterns made in GH to add texture or patterns for SolidWorks models, but was mostly unsuccessful. Any tips? I work with a lot of people who use SolidWorks. Like we have some clients who send us stuff in SolidWorks, and then like we do things in Grasshopper for them. I think the main issue is like when you're converting like solid model to here, like the best file type that I've always worked is like the if I go to import and I try supported files, I think it's like a IGS, yeah, IGS file. Those seem to like work really well. The poly surfaces come in like not flipped and crazy. For some reason, sometimes the step files don't work so well. I think IGS is the best file type to transfer from SolidWorks to Rhino, at least in my experience. I don't know what else would be unsuccessful. Just gotta try to figure it out.
And do you have any resources about developable strips?
No, not really. Like I didn't really. No, I guess not really. No,
Yeah.
I mean, go onto the Grasshopper forum and search like Daniel Piker developable strips, or just like developable strips, because like I think I've seen him post some really cool stuff about it. That's why this is when I was talking about Newhouse, because they've also done some cool stuff. And I know the guy on Newhouse has an account on Grasshopper forum, and he's posted some like interesting stuff that they've done. So if you search around the Grasshopper forum, you should be able to find
What is it, like PNU house?
PNEUHAUS.
PNEU.
And their website is like new.house, which is like pretty cool. Is this the
Oh,
same
yeah.
techniques you use on your catenary MST Pavilion? If not, how did you do your MST Pavilion? Oh, that was like, I posted on Instagram about that. That was like when the ideas were churning, kind of. And that's what sort of gave me the idea for this. No, the way I did that was I generated a minimum spanning tree of some points on the ground, and then like inflated a mesh from there, like upward catenary weighting kind of thing, and then duplicated that mesh, and I had one in the warp direction and one in the weft direction strips, but those were quads, and I planarized that one. That one was easier to control, like the directionality and like the like rows versus columns of the strips, and so I could like color them differently. That's like probably how the Very Many does like stuff where they can get each layer to be like the right colors and perfectly ordered, etc. So this is not so similar really to that. No, it's not really similar, except it's strips. So it's kind of similar, I guess. It is a little similar.
Okay. We're a bit over, but if anyone else has a quick question or wants to jump on camera or voice,
Come on, somebody jump on camera and ask a live question.
now's your chance, or forever hold your peace. But in the meantime, yeah, again, it was really, really awesome. For everyone that's here currently live, you'll get an email afterwards when the recording is ready. It takes Zoom some time to process it. So once that's done, you'll get that. And then the file is already in the same Dropbox, so you'll have that already. And let's see. What are the commercial applications of the Grasshopper work you do? Well, this is one of them, no?
This is one of them. Some installation design. We work with like architectural firms, engineering clients who need things done. Like, let's say they use SolidWorks a lot and they like need some funky stuff and like really hard to do in SolidWorks. They turn it over to someone who does Grasshopper. Or we work with people who do a lot of fabrication, and we like automate their fabrication drawings and like DXF export for like the cut lines and stuff for like a CNC router. We can like automate these things that these people do. So we do a lot of automation of fabrication data and funky design stuff when people need like some interesting things designed that they can't do in traditional CAD programs. If we had more than 3 types of holes and we wanted to mark up holes, should we put hole numbers on the other side of sheets? I wouldn't try to flip things. It's just a little hard.
Yeah, because you won't be able to see.
Yeah, it's a little tough to
because by the time
to fabricate both sides, like laser cut and align everything perfectly. But also then, yeah, when you're putting it together, that stuff is going to be on the inside of the thing. So a little tough to look inside and see the name. I would just put it like very small. Or you could have like in the hole, you could have like a little, let me change the color of this layer. You could have a little like flap, like this on one edge of the thing with the layer, with the whole typology name. And then you could like fold it inwards, after you put it in so they can't be seen. Something like that maybe would work. That would be one way you could do it. Is it fine if we mail you guys if we get stuck somewhere?
Yeah, I mean, we can't promise how attentive we'll be to it, but might as well try. You can email us, and if it's necessary, we'll email James or ask James.
Yeah.
Or I don't know if James, if you're open to people just writing you on Instagram.
Send me an email or send me on Instagram if you are stuck on something, for sure. Yeah, on Instagram, I'm at James D. Everyone always thinks my name is Jay, but it's not. Wow, that was an amazing stream of consciousness. How much time did the original programming take for this process? Okay, so the thing about this project is we did it all in 1 month, just 30 days. We were the subject of an artist residency where we had 30 days to design and program and fabricate and install and exhibit. This whole thing only took 30 days. So probably 20 days were spent on, or like, let's say, yeah, first 7 days, probably all design and just like iterating and like drawing and sketching and things. The next 10 days, probably 10 to 15 days programming. Then the last like 10 to 15 days of the month are all fabricating. And then the last like 24 hours, we're just like installing this thing. So it was a pretty fast process.
But you just go through it, and then like every time you're like, well, now I need to label, just work through it. Okay, now I need to fold these things, and you just work through it.
Yeah.
It's like, it's a process. You run into problems and then solve the problems, and then that causes more problems, and then you solve those problems.
Exactly. I would like to get connected. If at all you're interested in some commercial long span roof projects, absolutely send me an email.
Of course he's interested.
Of course I am. Send me an email to james@emergent.design. Send me an email with all your business questions, and I will get back to you for sure.
Yeah. And check out James's website too.
Yeah, emergent.design.
Okay, so I think that's it. But we have from Keza, who was asking how to jump on camera. And I don't know if they still want to jump on camera. If you're there or listening. There we go.
Yes.
Promote. Okay, so they'll be coming in here.
Cool.
Here we go. Hello.
Hi. Just a second. I'm trying to find it. Oh, there we go.
Hello.
Hey guys.
Hello.
I guess I don't really have a super good question. I just wanted to say that like I'm an industrial design student, and I'm really excited about computational design, and it doesn't really get taught. Like I feel like being a computational designer is like this like really brand new thing. And I was actually recommended to take this course by a professor who taught a computational design class, but it was in the School of Architecture, not in the School of Industrial Design. And anyway, I just wanted to like come on here and say thank you. And like, as an industrial designer, like we do CNC and laser cutting, but like how that ties into fabrication and using the computer and all this stuff. So I guess I was just gonna say, as a student trying to learn more about this and not really having like classes available at my institution, I don't know how other institutions are, like where's a good place to learn other than coming on here and like doing these kinds of things? And like, would I need to learn how to code to get really good at doing this thing?
Yeah, I mean, it's interesting because, I'm at Nike now, and I was architecture before that. And honestly, I think computational design is just like made for industrial and product design. Like, I honestly think it has so many more applications than architecture, but it's taught so much in architecture, and like almost no one in like product or industrial design even knows about it.
Yeah.
They're still doing like sketches and this and that, and it's just like so like crazy to me because yeah, I mean it's just like somehow I feel like it ended up getting popular in the field that I think it's not necessarily the most useful or even the most interesting in. Um, because when you use it in like architecture, you're doing things that like facades or layout optimizations, or, so it's not really it's not really even things that people could see and touch. It's a lot of like behind the scenes stuff. But I think, in products, it's just like so many uses for it, from like aesthetics to manufacturing. So it's a good point. And if you want to learn more, it just depends like what the level of learning you want. Like for instance, we have our design morphine, like we opened up an accredited master's degree program that starts in September, and it's based on computational and advanced design, not architecture or computational. Like so, it's looking at all kinds of things computational. I think there's not many schools that get like most of the schools I know that are doing like computational stuff. There's like ICD, AA, like all these schools are really great schools, but they're heavily focused in architecture.
Yeah.
And it's like if you don't want to be an architect, it might not be worth your while to do that. So it is hard to find like an actual like degree or school in computational design right now, like detached from like strictly architecture or pavilion related things. So we have one. I'm not sure about others that are attached. Also, things like these kind of webinars. You don't need to be a master coder.
Yeah, I only started coding like 2 years ago, and I've been doing Grasshopper for like 8 years prior. So
I mean, I can't even say that I'm an amazing coder. I'm just like a good Googler. I mean, if you're good at Googling, like you can solve most things because chances are someone's had your problem before.
Yeah, for sure.
Yeah, I didn't want to get too deep into coding, especially if it wasn't like design oriented. And a lot of like, coding camps or people who teach it are not really teaching it for like design purposes, or at least not like fabrication design.
Yeah, it's tough.
It's not 100%. It's not necessary, like 100% necessary. I mean, computational design is like, it's more like a mindset. It's just a kind of problem solving.
Yeah, you don't even need to use a computer to do computational design.
Yeah, which is strange.
You can compute analog.
Yeah, it's just problem solving, and there's so many tools like Grasshopper that make it so that you don't need to code. I mean, James did some coding here, and every plugin that's made you can do in Grasshopper if you really, really want to. You could annoyingly and
painstakingly
go through it. But
absolutely. What school do you go to? What professor recommended to you watch this?
I go to the University of Houston, and Andrew Cudless recommended this
I know
course.
Andrew,
I don't know if you guys,
Awesome.
And he's amazing, so he got me into this, and it was really interesting. As a freshman or sophomore, I did a parametric chair, like where the slats of it, and I did it all in SolidWorks and had to like model each layer individually and then like CNC each layer individually. And then I took his class as a senior, and it's like day one CNC bench. It's like baby's first computational design. And like
that sounds painful.
Pseudo computational.
It's like so easy. And I remember like painstakingly like wasting weeks and weeks and weeks of a semester trying to figure out this like parametric bench. And I saw them everywhere. So I'm like, they must be easy because they're everywhere. And not understanding why I didn't get it in SolidWorks so quickly. And then it's like, oh, Grasshopper, of course. Like, and then it just like something I wasted like 4 weeks on happened in like 20 minutes. So it's kind of
in my school days. I mean, I had a similar experience. I remember our kind of first experience with Rhino Grasshopper. We were kind of given an assignment, like we had to take a tower and model it, but we weren't really given like how to. And it was that tower that has like the square cut out at the top of it. I forget the name of this tower. It's kind of like twisty a bit, but anyway, So like that whole week, everyone was like looking online for plans, like drawing every plan, like extruding the plans and like doing this thing. And it took everyone like hours and hours. And then we went into class the next day, and the professor showed us how to do it with Grasshopper, and he did it like he just made like the base shape by like lofting and then like booleaned out the floor slab, and it was like 2 seconds of work. And it was just like, and then just like cut out the square at the top, you know. So yeah, it's anyway. Thank you for joining and coming on live. I'm glad you enjoyed it, and reach out to us if you need help with any other resources or suggestions.
Absolutely. Yeah, if anyone is also like making anything or like posting stuff about this on Instagram, definitely tag me. I'll share it for sure. I wanna see all the results, you know, from this webinar.
Awesome. Well, thank you guys so much, and thanks for letting me come on. I really appreciate it. And yeah, it was a great show.
Thank you. Stan asks, how many are you in your firm, Emergent Design? Who are the partners or key employees? It's me and my partner, Jason. He's the more architectural knowledge, and I'm the more industrial design, product design knowledge. So we combine, just us two. When we have projects that like we need some extra hands with, we do have some friends who like we went to school with who we feel comfortable jumping on with. What is Jason's last name? Well, Jason Haskell. Maybe you know him. I don't know why you're asking me that. Jason Haskell and me, James Dalessandro. We are Emergent Design, just us two. That's all it takes. Yeah, get the Bible. AAD Algorithms, AAD Design, Parametric Strategies Using Grasshopper. Really good book.
Yeah.
I have it on my shelf. Have I read it all? No.
I'm in that book.
Oh, really?
Yeah, I'm credited there in the credits page.
That's cool.
Yeah, also check out our resources page, because we have, you know, we've collected like what our team thinks is like the best, like kind of intro courses. To me, still the best intro to Grasshopper is Mode Lab.
Yeah, agreed.
And it's from 2015 and still more relevant than any of the new ones, because they're just so thorough.
AED, Algorithmic Design, Parametric Strategies Using Grasshopper. That's the name of the book. Some workshop on Blender.
Blender, we don't have any, but there is intro courses on our resources page if you want to check those out. The reason we don't focus on Blender so much is because it's not really used in a professional or career setting so much.
Not in like these fields, not in like things that need to actually be made. In like character design and animation, professionals are starting to like use Blender, and it's definitely powerful for that. But for things that like really need to be made, Blender is like kind of not the best for it, because it just uses units. It doesn't use like feet and inches or anything like that. So it's not like
I guess
really great.
The other problem is like that whole industry's been trained since birth on like 3D Max and Maya, and I guess if I mean I know already like Maya, and if you know it, like if you know one mesh modeler already, you don't need to know 10 mesh modelers. I imagine Blender being like adapted by like younger companies, you know, like where everyone's kind of new and young
and broke.
So
it's free, and that's like
we might do workshops on Blender at some point. We just haven't yet, but there's the intro courses there.
I do like Blender a lot, and there's some really cool tools like Alessandro Zamparelli made Tissue for Blender, which is like the coolest ever. I still use Blender all the time. I use it every day whenever I need to do like a rendering. It's my go-to like rendering software. I always make all my renders in Blender.
I have nothing against Blender, or I mean software is software. I'm just saying like the reason why I think it's not like socially acceptable in the workforce yet. It's just because all the old guys have been, guys and gals been, using Maya and Max forever. So
He says combine Keyshot with Maya, and it turns out to be Blender. Maybe maybe someday. I know there's some stuff Maya does way better.
I mean, I'm personally like many hours a day Houdini these days. So
nice. Thank you so much for the resources page. So helpful. Good. Would you please share the link of the final files? It's the same link that's been there from the beginning. It's the same page.
Yeah, it's the same, and it's also in your email as well.
Mm-hmm. Could we fabricate a small project using this code for sure with a modification regarding our material and mention you as a resource? Think so, unless you sign something in the Design Morphine workshop that says you can't. I think you can. Right?
That's up to you. That's your design.
I see. Yeah, well, don't just recreate what we did here. Don't copy my thing. Don't take the files that I put in the download folder and just make that.
I mean, you can see if you're. I mean, we have whenever you sign up for anything, there's always this click, and you have to confirm terms and conditions and all that. So I suggest you read that, and if you have any questions, that's to protect our tutors and their work. So it's important to always read through those things before you do something like that. It's there anyway.
As long as you don't just recreate this thing or correlate, and you're just using these techniques you learned here, then of course you can do that. That's the whole point of the workshop, is so that you learn techniques.
Yeah. That's it. Yeah, and that's basically what terms and conditions says. You can't use the exact provided thing, but you're allowed to adapt and remix and whatever.
Yeah, exactly. Cool.
It's never cool to copy without credits.
Thanks a lot, Michael, for inviting James. Learned a lot. Agreed. Thanks, Michael, for inviting me.
Agreed that I learned a lot.
I learned so much. I was a little worried when that first C# component didn't work, and I was had to go on the fly. So I did learn a little bit.
Yeah. All right. Well, I think we should end this thing before we get too carried away, because we could just sit here and talk all day and be fine with it. But
Yep.
Sure, we all have things to do. Thank you all for attending, and don't worry, you'll get your recording, you'll get your files. They're there. Reach out to us if you have any doubts, problem.
Somebody asked if we can upload it without the timer. He's having trouble uploading Strip Making Final, but Strip Making Final doesn't have a timer in it. So restart your machine or something. All right. Thanks, everyone. This is really great.
See you, James. It was awesome.
Bye.
Bye.